Hi, everyone. Welcome back to another day of TensorFlow Everywhere, produced by the North America Developer Ecosystem team. I am Kyle Paul, regional lead for developer ecosystems here in North America, and excited to have all of you back again today. Thank you for joining us yesterday. Hopefully you got a lot out of all of the wonderful content we had. There's a lot of great questions, a lot of amazing speakers. And so hopefully we can do you all a great service today we have all the amazing lineup of speakers that we have again today. I know I'm very excited. There's a lot of great content that we have going. But to kick off, just as a quick reminder, we kindly ask that everybody follows our code of conduct. You can find the whole thing here on the website. But you can make sure to keep the comments clean in the chat box over there to the side. If you see here or anything, you could please feel free to reach out to us. I have our email address there at the bottom of the screen. We're more than happy to hear your questions, concerns, any issues that arise. Please don't hesitate. But it comes down to some basic fundamentals. We're all here to learn, have a good time, network with each other. There was a lot of great networking going on yesterday, so hopefully we can help inspire that again today. But basically have a mutual respect for one another. We're all here to learn and share our knowledge. We don't anticipate there will be any issues, but again, there's a way to contact us there at the bottom of your screen. Again, on social media, there was a lot of great tweets out there. So please continue to use the hashtag TF.Everywhere2021. We've been seeing a lot of great stuff. Don't forget to go ahead and tag at Google Devs and at TensorFlow. We'd love to help these teams know what we're doing here in North America, as well as help highlight some of the stuff that you're excited that you're learning here today. If there's a favorite speaker you have, or your question happens to get highlighted, anything fun like that, we'd love to see you tweet about it too. With that, as I mentioned, I'm on the developer ecosystem team here in North America. Just as a quick reminder, we aren't necessarily tied to one product area or another. We help access all product areas here at Google. And so one of the things that I really love about my job is I can help with product feedback. So if you have any feedback about a product, feel free to reach out to us. Something isn't working right, or there's something that you really do like, we're more than happy to bring that back internally to the various teams like TensorFlow to let them know what they're doing right, what they could be improving upon. And the other thing is, we get to host events like this or bring content back out to the developer community to help highlight and share what are some awesome things that you can do and build with TensorFlow. On the developer ecosystem team, we do have many different community programs that you can become involved in, such as the Google developer groups, which are available globally. You can reach out, learn more about Google tech, such as TensorFlow, Google Cloud, Android, Flutter development. There's all kinds of stuff in a community near you there. And then we also have the Google Developer Expert Network, which highlights individuals out there in the community that are experts in XYZ Google technology. We have a great lineup of more Google Developer Expert speakers again today. And you'll get to hear from one up next. Then we also have our Women in Technology, the Women Tech Makers program, which highlights and empowers women in technology and give them a voice and a platform to learn, share, and a community to come together in. We also have our Entrepreneurs Accelerators Network, which helps highlight and empower startups around Google Cloud technologies. And then, of course, we have our University Students Program, Developer Student Clubs, which brings together a community there on campus at the university or college to come together around Google technology and learn and grow with each other on that one. But to dip in a little bit more on the experts program, like I covered yesterday, we are looking for more experts. So if you or somebody who is a Google developer, a potential candidate for the Google Developer Expert Program, let us know. These individuals typically have characteristics where they enjoy sharing their expertise out with the community, other developers, startups, stuff like that. How to be eligible to apply. You obviously, beyond being an expert in the topic area, these developer experts, they write technical content such as tutorials that they post on a blog. They help write code samples, books, as we saw with a lot of our GDEs yesterday. They're authors of multiple books on TensorFlow and versions of that. They also mentor the tech community, as I mentioned, other developers, startups, etc. They are also recognized tech conference speakers. So like the event here today, we help give them a platform to speak about tech, but there are a lot, we acknowledge that there's lots of other technical conferences out there that they could speak at, and we want to help highlight and boost them there. As well as being clear in communication and providing meaningful advice. Being a part of the Google Developer Expert Program, you receive acknowledgement by Google. So many of them have on their profile pictures a little badge that says that they're a Google Developer Expert. There's invitations to join projects and access to Google Teams at within Google. And this is to where you can help provide early access feedback to things that we're working on, or you're able to provide firsthand experience like, hey, this is something that we're using out in the field with TensorFlow, and this is this can be improved. And so as a Google Developer Expert, you're able to work with the engineers and developer advocates that way. And then on top of it all, you have access to a global network that's growing, a growing global network of these Google Developer Experts in your field, as well as other pillars within the Google Developer Expert Program. Some of the resources, if you want to learn more about the Google Developer Expert Program, and see what other Google Developer Experts are doing out there online, we do have our website where you can learn more about the program, the Twitter, which we highlight and share some awesome stuff that our Google Developer Experts are doing out in the community, as well as the Medium blog, where we allow a lot of our GDEs to be guest blog posters and stuff like that. So you get to see a lot of the cool tutorials that they're building or insights that they're sharing about Google technologies. And then last but not least, our LinkedIn channel, where you can see and interact with different Google Developer Experts there. If you or anyone that you know would be interested to apply, please come chat with us. This is the link to the application form. Do take your time filling it out. It's not something to quickly run to and fill out. It does, do spend the time to fill this out. There are many steps in there. Don't leave anything blank. If you do have any questions about, do I apply, do I fit for this program? Is it something I should go for? Please reach out to us as well. That, I'm more than happy to chat with you, see, is this something that you're a fit for? Is this something that, your skill set, works with and stuff like that. So more than happy to chat about it. I do know many of you have reached out to me already on LinkedIn. I will get back to you, but yeah. And then we also want to help and recognize our TensorFlow user groups out there. And so we know that there are a few of you here in North America, and definitely many around the world. If you are interested in learning more about TensorFlow, there is likely a user group near you. If there isn't one near you, you can definitely start one up, and we'd be more than happy to help grow and you to join the community and help you grow. The link is here, TensorFlow.org community groups, and very excited to help promote this community out there. As part of your registration, many of you asked a lot of great questions. We may not get to all of them, but with these questions, it did help shape our schedule. So thank you for providing some great feedback in the registration. We do have some of those questions pulled up, but continue to ask questions in the chat. There's lots of awesome stuff that these speakers will be talking about today. And so you'll see this banner pop up a few different times. So we will be taking live questions. There is a section at the end of every speaker's talk where we will be able to pick some questions from the chat. So go ahead and do that. And as yesterday, we announced this, many of you were also looking for more hands-on workshop style learning. So we do have this free hands-on learning provided by Quick Labs. The link does expire on March 6th, so make sure to redeem it sooner than later. All you have to do to redeem is, hit that link and then, complete the very first lab in the quest that's pulled up there. Once you've completed the first lab, you'll receive the additional credits to complete the rest of the quest, and then be able to, do more learning on Quick Labs for the next 30 days. So it's a lot of awesome stuff there. And this is learning on GCP, learning on TensorFlow. There's other machine learning labs that you can take on there as well. So it's not just TensorFlow, it's not just GCP. There's lots of other fun, enriching learning there. If you do happen to run into any issues whatsoever, please reach out to support@quicklab.com. Note there's no S on this one, but support@quicklab.com. They're ready, and they will be more than happy to help address any issues, whether it's redeeming the code or you get stuck on a lab, anything like that. They're here and waiting for you. And then finally, some housekeeping items. If you need the schedule at any time, we will be posting it in the chat occasionally. You might see this pop up on the screen, but if you want to see who's up next as a speaker, anything like that, you can always have the schedule pulled up in a second tab. TF Everywhere-schedule is how you can find that. And as always, I will be throwing this up between every speaker as well. We do appreciate your feedback. We had a lot of great feedback from yesterday, and we continue to appreciate the feedback that comes in, not only for us, for how we run this event, how we put everything together to provide you more great content around TensorFlow, machine learning, etc. This feedback also goes back to our speakers as well to help them improve and grow as speakers. So thank you again for all of that. And without further ado, I'd like to welcome our next speaker up, who is a Google developer expert, Vikram. He's a co-founder at Omni Labs, where he helps build the future of work. What he'll be walking us through is how to be Bach on a budget. So up next is Vikram. Take it away.
Fantastic. Assuming I'm live, let's get started. Good morning, folks. Thank you for joining us today. My name is Vikram, and I'm co-founder for Omni Labs, where I handle all things tech. I'm also a Google developer expert for cloud and machine learning. So feel free to ask questions about cloud and how to use machine learning on cloud even. At Omni, we are working towards building solutions for personalized process automation. We are looking for our next passionate engineer to join our team. Help us build the future of work. Feel free to reach out to me at vikram@omni.com or send your friends my way. I'll be happy to talk to them. Now, long before we started Omni, I had a dream. The dream was to become a rock star. I'm sure you had the similar dreams. You had similar dreams. If you had similar dreams, you are in the right place. Please let me know in comments about how it worked for you. But let's take a look at my journey. So when you look at it objectively, you don't really need a lot of things to become a rock star. First, you need a guitar, hopefully an old guitar. Get some practice playing it with your band. So you need to practice with your band and figure out how it works. All the synergies need to happen. And then you need to finally, once you are good enough, you play at the world stage. Fortune and fame, that's all you get. Nickelback gave me high hopes. But it will be an understatement to say that music sense was just not into me. Things just didn't pan out well. This is how it went. So I had to rethink my life choices at a juncture where I really want to be a rock star, but I just don't really have that in me. What do you do? So I started pivoting and focusing more upon my engineering skills. During that time, I came across the concept of sound. I'm sure all of you did some basic physics, and in that you can understand, you must have learned about this, that sound is just a disturbance in the force, not the force from Star Wars, but mostly the particles that are around you. And it's just the variation on how they work. So what we can do is, I thought that can we actually make a music out of that? So programming to the rescue of my rockstar career. what I want to do is I want to create a music. So how do you do that? Music is essentially just make some noise, some random variations in audio, add it to a timeline, and add some variations. And that's generally music, if you try to boil it down into a few simple things. So how do we do that? Good thing is JavaScript and programming, to rescue, of course, can allow you to do that. You can generate tones, then add those tones to a timeline, and then randomize it. These are the three simple functions that we need. And we can have a machine that can make music. That sounds fun. Should we get started? Should we try it out? Just so we know, the code is fairly simple. JavaScript allows you to do this with audio context. Audio context allows you to tap into the audio devices of your machine, and then you create an oscillator. Oscillator essentially oscillates the waves. Then you can specify a type of oscillator that you want to use. So there could be multiple types of oscillator. The most common ones are sine and cos, of course. Like, just think of all the geometry that you learned, and that's how you can oscillate a wave. And then you connect it to an output device, and then you can play it. You can stop it, of course, simple things. Let's do it. Let's do a quick demo of it. So I built a machine which can make music for me. Maybe what I can do is I can just play this machine and then be in the background and just wave my hands over a guitar. Maybe that would work. Okay, let's try. Let's see if this machine actually works. So we talked about waves and oscillator waves and how those work. So let's see what those waves are and how do they sound like. So I'm going to mute this, and then you can play. Okay, so this is a sine wave now. Let me increase my audio. This is a sine wave. You can also generate square waves. You can generate triangle waves. Similarly, sawtooth waves. Now you can mix and match around here and try to generate different types of waves. But just the waves themselves won't do enough. We talked about that. We need some frequency modulation in there. So let's add some frequency modulation, and then you can generate actual keys that you hear in the music. So let's generate C4, which is a frequency modulation as 261 Hertz. Same goes for A4 now, 440 megahertz, not megahertz, hertz. And then G5. I don't actually, so this is the extent of my music career. Like, I don't even know what G#5. I can't, like, yeah, you know it now. So you can modulate frequencies. So we have waves, you have frequencies that you can modulate them. And then using those, you can actually start creating sounds that sound from as if an actual musical device. So let's see this. We are mixing and matching our waves with frequencies to generate different types of musical sounds. It's a square, there's a sawtooth, there's a triangle one with different frequencies. So essentially, you have three variables that you want to mix and match and generate different sounds. The first variable is type of wave. Second variable is the frequency. And the third variable, which is not shown here, is the time, pinch of time. Just add that, and you can generate a sequence. So music is not just one instance, because like what we are doing here is just this one instance. You want to add it to a timeline and then generate the music. So let's try generating the music. Now, I don't know about you, but for me, this is very much reminiscence of Nintendo DS and playing Mario and Pokemon and things like that. But this is still not music. It doesn't speak to me. It's just like too random, I guess. You see the issue, right? I'm sure it doesn't speak to you either. If it does, great. Like, I can publish this and I can become the rock star. But I'm sure it doesn't. Okay, so let's go back and assess our situation. It doesn't speak to me. Of course, we just talked about that. So let's assess the situation at this point. Here are some challenges that we ran into. The issues are, like, complex sounds, like drums, are very hard to recreate. Now what I have to do is I have to figure out exactly how a drum sounds. I need to change the frequency. I need to change the timeline variables. I have to play around with different types of chords, different types of frequency and waves, and try to come up with the correct drum sound. And even then, I need a vast library of these things. And exactly how do I place them together? So order of placement of these stones matter a lot. You can't have a really high pitch and then a very low pitch right after each other. You need some kind of placement. Sometimes they need to be very close together. Sometimes they need to be spread apart. And that order of placement, it's not there yet. And I can write functions for those, but it just might take a lot of time. Then pure randomness is also really bad. Like if you take a look at that code, the code is open source on GitHub. If you take a look at that code, it's just purely random. After every few seconds, I'm just playing out a tone, and out of a random library of frequencies and waves signs that we have. So it's not really good. It needs a personality. It's just pure randomness. So I spent a lot of time at this point. I was trying to figure out how do we make this work. I remember at a time spent reading 10 different papers on generating ordered randomness and entropy of the system. And that's how I somehow got into cryptology. But anyway, this did not work. So I was stuck. I was thoroughly stuck. But time is the best way to cure those all. Years went by. Then one day I came across this. It's called machine learning. This is not totally unexpected because it's been around for a while. It's been around even before I was even born. So it's there, but it wasn't really feasible until at that point and wasn't much widespread in the use. Also, the concept of deep learning was just starting to take shape at that point. So how do we make it? How do we use machine learning so that we can use machine learning to generate music? Can we do that? But first, let's talk about what is machine learning and how does it differ from normal programming that we have been doing? So the traditional programming, as we just talked about a few seconds ago, example that I gave, is we have some rules. The rules of generating music were that you have waves, you have frequencies, and then you join them together to generate music. So we have rules which were you combine frequency, time, and waves, and then data was the types of frequencies, types of waves, and then we did our traditional programming to join them together and generate the answer of music. That's our traditional programming route. Machine learning just tweaks it a little bit, where you don't really write the rules. You let machine figure out the rules, and you just provide samples of answers, samples of data. And then that machine tries to use those details to figure out the actual rules. This focus on letting the machine figuring out the rules. So the equation just changes a little bit. Now, that's fine, but what is deep learning? Deep learning is just a specialized form of machine learning, where rather than having just a single layer of trying to figure out what is the logic, we use multiple layers. And these multiple layers have neurons in them. Neurons are just essentially a unit that can learn, that can understand some value. We'll show more details as we go forward. So what deep learning allows you to do is allows you to have multiple neurons in different layers. And each neuron learns something about the problem. And at each layer, you try to abstract away the problem. In naive terms, they act as filters. Each filter gets trained to allow only a specific type of data to go through. And with multiple layers of such filters, we get the result that we expect. So in this example, we have an image of cat versus a dog. And we have an input layer, which takes in the image, and then multiple layers of neurons. Those neurons get activated based on what is in the image. It could be color, it could be the edges, the shapes, and things like that. And finally, we get a response, whether it's a cat or a dog. So you can actually try these things on your own. It's fairly easy. This is Google's playground. It's called playground.tensorflow.org. And you can try your hands upon playing with different features and trying to generate a machine learning model. Let's give it a try. OK, so here we go. We have a problem. The problem is we have the blue dots and the orange dots. And we want to build a machine learning model that can distinguish between these two. So here are our inputs. These are two very simple inputs, which is one input is vertical line, another is horizontal line. And with these two data inputs, we are trying to build a model that can distinguish between blue and orange. Actually, let's start with a simple example. This might be much simpler. Now you can, if I were to draw a line for distinguishing between a blue and an orange group of values, I think the line we can very easily draw is here, right here. If I draw a line here, that'd be great. That's it. Now you can train a model, machine learning model for it. The model essentially will start with this, and then we can see how it works. So fairly quickly, within some 30 iterations, it was able to figure out based upon just these 2 iterations. And this is our deep learning model with multiple layers. We have 2 layers in here. What it did was it said, okay, vertical line can be broken down based upon the data, can be broken down into different types of features. And the feature that it came out with at one layer is a slanted line. And similarly, a different angle slant, a different angle slant. And similarly and came out like finally on the output layer, it came out with these slanted lines, which depict it properly. And it's not a completely straight line. You see there's a curve in here. So that actually gave it a good way to build a model. Another one, let's try with this data set that we just talked about. So we'll try to use the same methods and same layer, same deep learning model, and then we'll try to see how quickly it comes up to get the result. All right, it was actually fairly quick. Within 80 epochs is the complete iteration from the start to the end of one training iteration. And we have done 80 of those now. So we passed our data 80 times through our model to get this value. And these are our inputs. So again, with 2 simple features of straight line and vertical line, we were able to combine those into forming a complex deep learning model, which can distinguish between those values between like blue here and orange. And this time the boundaries it drew are really complex, but you can fairly easily understand how it came to that conclusion because it built this bluish one. And then you can see that it went through a slanted line. So it's trying to actually build a circle over here, but it can't really do that. And over here, it's actually trying to form 2 different circles. You can see that like it has 2 different variations, and from that it has learned more details. So you can try to, if you keep going it around, it will actually try to form this, like you can see it here, it's actually trying to form a circle in here. So over time, it will learn more and more details and try to come to this, come to the final solution. Then again, we are trying with the same 2 features to solve this problem. And this time you see the same machine learning model. We haven't changed any of the inputs. We haven't changed anything in here in the model itself, but we just changed the type of data that we want it to work upon, and similarly the problem that it will try to solve. And now the deep learning model learned a different variation itself. Now, in this example, it's very easy to figure out how it's learning. In real-world examples, it's actually really hard to figure out what each layer of neuron is learning, but there are researches going on in those fields, and we are trying to determine those. But just for simplification, this is how it's trying to learn. So this time it started with slanted lines, and we can see here that it's actually learning these things. So like these 2 are exactly opposite of each other. And one neuron, even though it found it, it's like you can see that with the width of these lines, that's over time, this weight is going to get reduced. And this weight, 2.4, is going to keep getting increased as it goes through multiple variations, because it understands that this is the correct way to distinguish those 2. And this is the wrong way. Of course, it's the wrong way. It's getting orange on blues. So this is the model. What I would challenge you to do is, if you can, build a model with this. Now, to give you a short answer, you can't use just these 2 variables. You will need to find a new one, a new feature in here. And you might even have to increase the depth of your deep learning neural network. You can add more layers. You can add more neurons. I don't know how many you want, but it would be a good exercise for you to try it out. I'm going to give it a try. But you can see that it's not going to work right now. Like you can see it's not working. It doesn't know how to solve this problem yet. So this is just with 2 variables. I would suggest like try out different variables. And if you can make it work, ping it to me on Twitter. I'm happy to review those. And I'm sure you can just figure it out by yourself, but play it around. You can't break it. They promise it. I promise it. I have played around with it enough. But yeah, this is a good way to tinker around and learn these things. You can also try to increase learning rates. You can try regularization. You can try different types of problems even. Classification is the problem that we have been trying to do, classify orange versus blues. You can also type regression, try regression problems where you're trying to predict the values that might come next and not just classify between the existing data. So that's TensorFlow, and we just TensorFlow on a playground. We just went through that, but we also see that self-driving cars are being powered by machine learning and deep learning technologies. And somebody built a demo of using machine learning in your browser to train a self-driving car. Of course, these problems are not as complex as you would see in real life, but it's actually a good enough concept that you can do this in a simulated environment. And if in simulated, you can try to do this in real-time environment as well. Now, all of these examples are powered by TensorFlow.js, or simply as I call it, TF.js or TensorFlow.js. TensorFlow, hopefully you are familiar with it. We did a good session yesterday, all of the experts in there. TensorFlow is a machine learning library. TensorFlow.js is just an abstraction of that in JavaScript. Now, maybe it's just me, but JavaScript, I really like it. I know JavaScript as a language has its quirks, and I don't know if you have seen this, but there's a big book which says JavaScript in depth, and there's a very small book which says how to use JavaScript without running into all those gotchas. So if you know JavaScript well enough, and even if you don't, you can't really make much mistakes in here. So what does TensorFlow.js gives us? It allows us to run existing models. So you can have an existing model that is built for you by TensorFlow team or other teams who are building these models for you. And these models are pre-packaged. You can just import that model and start running. We'll have examples of these in a minute. You can use existing models, or you can retrain existing models. So most of the machine learning work has been done in Python up to this point. And even right now, it's fairly focused upon Python. You can take that model, convert it into a TensorFlow.js model, and use that. You can directly convert that existing model, or you can use transfer learning to retrain it on your own data. Then finally, you can also write your models in pure JS. So let's see it in action. So this is an example where we are trying to use a model that is built by TensorFlow team. How do you use it? This is a very simple web-based example. We start with a script import, where we will import the TensorFlow.js itself. Then from our TensorFlow models repository, we are importing a model for toxicity detection. This is just for the text toxicity, not the image. Then we wait. Very simple programming interfaces. You use await to load the model. It will fetch the model from server side, load it into memory. If it already has it, I'm sure they have done this, where it will automatically use the local cached version of the model. And then all you need to do is call the model with classification of what you want to classify it as, and it will give the result of what type of toxicity it is, if it is a probability, if it is a match or not. Let's try to play it around. So I just ran a small demo on this earlier. That it sucks because of COVID that we can't be together. I would have loved to do this in an actual setting, in a physical setting, but we can't because of COVID. So when I run that, it's actually not an insult to COVID, COVID as a itself disease, or it's not an obscenity, it's not a toxicity. But if I just frame my sentence in a different way, the COVID sucks, you can see that very quickly it identifies that is actually an insult. There's some toxicity in this sentence that I just said. Even though the words suck and COVID are in both of these sentences. So of course, it's a machine learning model. It can learn these things better than just classifying these by hand. So this is a great example of using an existing machine learning model that you can use for your tasks. There are multiple of these that have been built by TensorFlow team. And if you have some suggestions on what you would want to see, you can reach out to them on Twitter, or even open a new issue on the models repository. Next, we have converting the models from your Python model into a JavaScript model, TensorFlow.js model. So for this, there's a simple TensorFlow.js converter tool. Now, last time I checked, that tool had some small bugs around models that are fairly complex on Python side. It would do great with simple models, but there are sometimes models which use APIs that are not conventional on writing TensorFlow code. So sometimes it would freak out there, but I think team has done great work on that, and you can easily convert a Python model directly into a TensorFlow.js model now. And once you have that model converted, you can use it inside your JavaScript app. You can package the model directly into the app, or you can fetch it from server side the same way we are fetching the model in the TensorFlow.js example earlier, TensorFlow models example. Now, finally, you can also build the model by yourself from scratch. So here, you're trying to build a TensorFlow.js model using the sequential API. So we start with TensorFlow sequential. It allows you to build a sequential model, a fairly simple, verbose API. Then we add multiple layers to that model. We add an input shape model, input layer. So we are adding first layer, which is a contour layer. We have a shape. This will generally, the input shape is same as the input that you're trying to provide. So this is an image-based model. So our input is width of image, height of image, and channels in the image, which are RGBA. So red, blue, green, and opacity. And then you're trying to figure out the kernel size. These things are fairly simple, and you can play around with these to figure out a good model that works for you. You can try out different activation layers, different initializers for your kernel, and then you can add more and more layers. So here we are adding a max pooling layer, and then we are flattening our model, or you can try out a dense model in here, and with a different activation at each time. Finally, once you have your model structure ready, you can compile the model. Remember to have a good loss function in there and a good optimizer. Now, the concept of teaching you how to build a model is kind of out of scope of this presentation, but I'm sure you can find a lot of examples around these. There's code labs that Kyle just mentioned a few minutes ago that you can play around with, and they all have like how to choose these different optimizers, different loss functions, and things like that. Then you fit your model. So we built the model code. Now you take that model code and fit it with the data that you have. And remember the example that we played around playground on TensorFlow. You have to run it for multiple epochs for you to understand and train that model. So you fit the model, you train it around. Finally, once you have the model, you can save it. Generally, I prefer to save it in local storage. You can save it anywhere else, like keep it in the RAM. But generally, it's a good idea to save it in local storage so that next time you don't have to redo the whole process. And finally, you have the model. You can just start predicting the model. Now, at this point, you can take an existing model that is built by TensorFlow team, take a model that you already have in Python, convert it into TensorFlow.js, or you can write your own models. I think that should be good enough for you to get started with this. But if not, let's give you some more incentives. So the reason I love JavaScript is mostly because you can actually run it everywhere. So of course, JavaScript you can run it in the browser. Most of this website that you're looking at is being powered by JavaScript. You can run JavaScript in mobile. You don't really have to do anything different for you to be able to run that JavaScript code in your mobile. You can run the same code in server as well, most of the time. Yes, of course, you have to convert from pure JavaScript into Node.js, but primitives remain the same. It's just like reading from files and local storage and things like that. Like some primitives change. Of course, you might want to use the Node.js TensorFlow library, which also allows you to use more resources and properly on the server side resources, like using your compute or like multiple CPUs or graphic cards and things like that. So it can allow you to do those kind of things. Then, of course, you can run it in a desktop app, Electron apps. If you're not familiar with those, you can build an Electron app, which is powered by JavaScript itself and Node.js, and those can go as a desktop app as well. Of course, it's not mentioned here, but you can also use Node-RED or similar technologies to build it into a model that lives on the edge devices. And same again, take the model, and one single model can be used across all these platforms because the underlying infrastructure is using JavaScript or Node.js to run those things. So that is one of the best parts. Then you can use that model. The best part is privacy in there. Like the data does not have to leave the user's machine. So let's do a quick review of how it works. So with TensorFlow.js, you have pre-trained off-the-shelf models. So models themselves are not just the code that we wrote, but you pass the data into it, you train it, you come to a good conclusion of this is a good combination of the data itself and the rules. This is a good set of rules. And depending upon the data that you have and the model code that you wrote and how quickly it works and things like that. So those are pre-trained off-the-shelf models that you can use. Then you can also convert Python models, train in the browser and Node.js, and use it, of course, and deploy it across various platforms. All profit. So all of that is great. That's just some good background onto that. But can we actually use it to fulfill my lifelong dream? You thought I forgot about that, right? No, I didn't. So let's see. Before we get into that, remember the problems that we had when we are trying to use a music making machine? We're going to try to fix those problems first. So the first technique that we will use is called style transfer. Remember that our music did not really felt like it had any soul. So now I'm not a god, I can't really build a soul, but best thing that we can do is copy it from somebody else. That technique is called style transfer. You learn, not you, your model. You don't really have to learn. You just have to learn programming. So you take a model, you take somebody else's style and try to train that into your model. And then that model can do the style transfer into your own data. So this is a really famous example. This is like very early in the days of TensorFlow, where it started with taking the artworks of historical significance and then using those to generate a style transfer network. And then you can convert those images into your own style. We can do the same thing with music. We'll see in a few minutes. So that's style transfer. Next, we have recurrent nets. So of course, we did not have a soul, so we can get a kind of a soul, or essentially a copy of somebody else's techniques into using a style transfer. But now, next part that we had is our tones didn't really have any rhythm to them. They just felt like random noise. So for rhythm, our model really needs to understand the temporal information. Temporal information in the sense of what is happening right now, what should happen next, and all of this in a time scale. And for that, recurrent nets are fairly good. So the examples that you're seeing in here is a user trying to draw whatever the prompt is, and then machine using the user's interactions to generate what should happen next. So user builds, for cat, user draws a circle, and then it knows that it should draw the ears next, and the eyes next, and the whiskers after that. So recurrent nets are great at that. You can use that. We can use that. So we'll try to do that as well. And then finally, remember that we gave up after a few tones because it was just fairly hard to write all the different tones to generate all the different drum sounds and all the different percussions and all the different piano sounds. It would have been so much time consuming. And of course, as all programmers, I'm very lazy. I don't know about actually all programmers, but most of them that I met, they're lazy, and I'm as well. So for that, we will use an autoencoder. What does autoencoder do? We'll use autoencoder, and specifically a variational autoencoder. A variational autoencoder allows you to learn, not you, the model again. As much as I say you, it's mostly the model that's doing the learning part. So autoencoder learns the nuances of the data in an unsupervised manner. So what you don't have to do is you don't have to figure out each and every type of possible features in your data. What you do is you allow it to get a lot of data, and from that data, it learns the nuances of the data in an unsupervised manner. So rather than teaching all the different strokes that we are trying to build here on how to draw a circle, how to draw a line, and things like that, it can learn those in abstract way. And finally, like just using all these human inputs, it can reconstruct those inputs on its own. So this is generally variational autoencoder. It actually works really well. You can see an example. I'll share the example links at the end. So at this point, it feels like we have solved all of the three problems that we had. We did not have a soul. For that, we can get it from style transfer. We did not really have a good timeline on how the music was working because it was just random. So we can use recurrent nets for that. And we did not really have a good library of tones and frequencies that we want to use. And we can use autoencoders for that. So do we think that we are ready? Combining it all together, can we get it done? Almost, just already, almost ready. So let's do one more thing. When we're trying to build these things, anytime we are trying to build a machine learning system, it's actually a really good idea to keep humans in the loop. It requires more effort from the machine and, of course, us to build those kind of systems, but machines can handle it. We have good enough compute. For example, in our case, what we will try to do is we will give our system, our machine learning model, two end results of an input, and it can generate a sequence that should fit in between those two. So we can give it a start sequence and an end sequence, and it can generate the variations that we should go through in the timeline to get to that start to the end sequence. That sounds good to me. Of course, as I said, keep humans in the loop. So we can give it a start sequence and the end sequence, and it will generate all the sequences that go in between. Now, when I started trying this, I was searching for different things, and I came across this project from Google. Of course, they did it. It's called Project Magenta. So Project Magenta is a project inside Google Brain team, which focuses on exact same things that we just talked about. They are a group of researchers who are also artists. Their work is focused upon generative model research. So using the machine learning to generate different types of things. It's not just music. It could be art. It could be a 3D model and things like that. And all of the work that they do, they put it in open source. How amazing is that? So I looked into their work. They do a lot of work here. They put creative tools. They build open source community. There's generative models research that you can use. And they have built out a lot of samples around this. And we will mostly use their samples today. Because, of course, again, I'm lazy. Just going to use theirs. OK, so are we ready to rock? Let's do a demo. First off, we will do, OK, no. OK, let's see. Let's start from the beginning. All right, we will do melodies. So right here, we are trying to build a model which will try to generate. Again, VAE here is variational autoencoder. So this is a model called Music VAE. It uses variational autoencoder techniques to generate music. So this is the timeline of how a sample is. We can get another sample. It's just randomizing this data. And based upon this input data, it is trying to generate a sound. Let's try to play it around. Now, I don't know about you, but that is fairly good sound to me. And to train this model, we didn't have to really write all the different variations of how to do a drum sound. And of course, this is a piano. So all the different keys of pianos and how do they sound and things like that. We didn't have to work upon any of those. And all you're doing is you're generating a random sample, passing it through the model, and getting the final example. And you can play it around. Let's get another sample. Just to play around, of course. Why not? So in this example, we are doing all of this only on piano. Can we actually try this with different machines, not just piano? So there's another example. I guess it doesn't work with the same tab in two different machines. Like these tabs are sharing data. OK, so here's another model where we are trying to use not just piano, but also drums. And one more thing. I don't remember exactly what it is. Oh, guitar, of course. All right, so let's play the sample. We just use the same music VAE model, but this time the data input is different. It's not just piano. It's piano, drums, and guitar. And we are trying to combine those together. Let's try another sample. It sounds really great to me. I don't know about you, but this is already amazing because what we have done is we have already used the two principles that we talked about. We are using a variational autoencoder to generate different samples automatically or learn different samples. It's not generating, it's learning those from existing data. I actually don't know what is a good way to say this because it's actually generating based upon the existing data. Anyway, and then second part of actually joining it across a timeline. So let's try another sample and run this along. So this is amazing, actually. Like, I don't know about you, but this is, for me, this does the job. We can just use this. But we talked about, like, we don't really have a soul yet. So for that, I promised in the beginning, being back on a budget, we will try to do what Bach has. So what we are going to do is, again, we as in Google, because Google already did all of these. So what Google did in this example is they took the style of how Bach created his music, and we will use the existing techniques that we know about, the variation autoencoder and the timeline, and apply the style transfer part in there to copy or use Bach's techniques to generate new music. So let's try it out. Okay, so again, all right, let's do it. We'll skip the intro for a second. Actually, let it go. All right. So what we just learned about music, what we're going to do is Bach has given us access to write at least one of his 4-part melodies. So what we're going to do is we're going to do one melody, and then Bach is going to use the other 3 melodies to generate the actual 4-part melody that he wants to use. So here we go. We are just adding, gonna add some random noise in here. All right. So this is a sample that we are giving Bach, and then you can use this data. Remember that things we talked about. Give it some sample, style transfer, all the techniques that we have talked about today. It's going to use all of those to build its own model and build a theme of Bach. So this was amazing. Like, as I can tell, as much as I can tell, it learned from the data input that I gave it. It harmonized it to generate a proper harmony, and it's playing that out. And as I promised, you can be Bach on a budget. You don't really have to do anything. You just use the existing model, train it upon a style of Bach, and you can just learn it. Model learns it, and it does that. It plays it around. So what's next around this? As you might have guessed by now, all of the instruments that we are trying are more classical themes and like simple instruments. There are only 3 instruments that we have gone through. So the goal would be in future to add more and more instruments to this, add more and more themes and styles to this. So right now we are talking about only classical music, because it's actually, the reason is that classical music is right now not in private domain, it's in public domain. So you can use that data to train your models. So as we see more and more music becoming available in public domain, we will see more and more themes and styles come in. And of course, variation autoencoders are great, but can we use generative adversarial networks, a different type of network, to generate these models, generate this music? Best thing that you can do, if of course not, best thing you can do, of course, help us with research and help build these kind of tools. But thing that anybody can do is help publish your music in public domain. When you publish your music in public domain, you allow researchers to use that music to train their models. So it's time for reflection. I'm actually low-key glad that I didn't pursue my dream of being a rock star. I would have missed out on meeting all of you fantastic people that I meet every day and do all the cool things that we do at Omni, and I do it in tech scene. I'm also very unsure that even if half of you would have come and attended my concerts. Yeah, fairly certain on that. If you have any questions or any compliments that you have for me, I'll take it all on my Twitter at Vikram Tiwari. Now, before you go, a few links for you. All the examples that we have played are open source and on GitHub, but the Midimi example is at midimi.com. Building an autoencoder. Now, this example is in Python, but remember, you can build a Python model and use the converter tool to put it into TensorFlow. So you can learn how to use Keras API to build an autoencoder. And then finally, this one actually want a demo. So you don't have to learn any of this. You can use Teachable machines, which is an experiment by Google, and build your own models. So let's try it out actually. So here's the Teachable machines. Teachable machines allows you to build your own model right here in the browser. So we're going to use the power of TensorFlow and build a model right here. It's fairly easy to do an image-based project, so we'll try to do that. Okay. So anything that we are talking about in models, there are different classes. So let's add the first class. We'll allow this. Do we have webcam? Okay. Oh, it's not using the correct webcam. Oh no. Let's try this out actually. I'm going to move the webcam. All right. Allow the webcam. Okay. So what I'm going to do is we're going to try 3 different classes. The class 1 is left hand, and then class 2 will be right hand. And then I'll add another class, which will be just my face. Okay, so let's try. So again, as we talked about, machine learning models need some input and some way to use that input, like some different types of input. So we'll try to give it input. So this is my left hand input. So we're just recording different samples of my left hand. Then we're going to give it an example of right hand input. So right hand, and then just the input of my face, hold it to record. Okay, good enough examples. So we have 48 images of left hand, 42 of right, and 34 of my face normal. Now we can train this model right here on this browser. This data is not being sent anywhere. All of the training is happening on the device itself. Don't switch tabs, it's trying to run. So it's running 50 iterations, 50 epochs, and within 7 seconds, our model is trained. And now it can detect that model. It can use these from these three different classes. It can generate a classification model. So right now it's showing me that it's 100% certain that it's my face and is in the view. Now, left hand. Now, right hand. Left again. And it's fairly fast. And the best part about this is you can export this model. You can export this model in TensorFlow.js format, of course. You can export this model in TensorFlow Lite format that you can use inside your Android devices as well. So if you are trying to build something very simple, you can just do all of those things right here on Teachable machines. And I would highly encourage you to try this out and try out different samples. Let's go to the home page. You can try out not only the samples with image data itself, you can try out musical samples. You can also try out, which is fairly common these days, is pose project. You can try out human poses. I know a friend who was trying to use this model to build a good way for people to exercise and to determine whether people are actually doing the exercise properly and your form and shape and things like that. So try those things out and let me know how it goes on Twitter @Vikram Tiwari. Finally, thank you so much, everybody. Let me know how it goes. World is your oyster. Go get it.
Awesome. Thank you so much, Vikram. Great talk and some really interesting examples there, showing off how we were combining music and machine learning and code. A lot of cool stuff. We will take a couple questions from the audience because we do want to be mindful of our next speaker's time. Because I know, let's try this one here from Manjunath. How do we know which frequency has to fix to that value? And I believe this is back to when you were demoing, the different frequency buttons. So like, how does that happen?
Oh, so it's actually all in the code. If you take a look at the code is on GitHub. I can share the link on Twitter. But each button actually has a function that it calls with the frequency value in it. So like it's actually like it's code, so I know exactly which button has which frequency, so I can tell you what to run. But the random example that is at top, it just uses different frequencies with different waves, and it just tries to use a random function to combine those together to run those. So yeah, it's just fairly simple. Like you can just take a look at the code.
Awesome. And I know there were many more questions in the chat, so hopefully you can stick around and answer those in the chat. I know our friend Jason was helping out with some of those too. This is one from the registration. What is the most challenging project you've worked on?
Ooh, that is interesting. Actually can't talk about that because it's a work project, but I can talk about the open source project that I generally worked upon. Yeah. So on open source side, I have been trying to work. I still don't have a solution for this, by the way. I've been trying to work around building a personal CRM system kind of thing. I meet a lot of amazing people, and I want to figure out how do I keep in touch with them. And the best way I have that for now is I just keep it in my contact book of who I met, where I met, and what kind of notes I have. It's just like not great. Mostly because I meet all sorts of people in all different social media platforms. So the problem that I'm trying to figure out is if I have the handle at Kyle Paul, like how do I match it back to the Kyle's Gmail address that I have or the Google address that I have? And how do I combine this together so that when I interact with Kyle on Twitter, I can go back and look at my summary for last month and see, hey, I interacted with Kyle on Twitter as well as on Gmail, as well as on these different platforms. And I don't have really a good way to join those together unless Kyle tells me that this is his Twitter. So I know exactly where to join it. But I'm trying to use some machine learning to join them together. I also play around with time series-based model, of course, generative arts. But though both of these, most of these techniques are openly available, and I can read research papers to solve those. But the project that I've been trying to do, I just haven't found any examples. If you have something, please reach out to me. I'll be happy to try to incorporate those. Yeah.
Awesome. Very cool. Excited to see where progress on that project, because that sounds interesting to me. I know there are other projects out there that have taken stabs at an idea like that, so it'd be very interesting to see what you come up with there.
Definitely, yeah.
But as always, it's great having you, Vikram. Thank you for sharing all these amazing insights. Everyone out there watching, don't forget to fill out the feedback survey. Remember that there's a 2 at the end of today's link. And thank you again, Vikram, so much for joining us today.
Awesome. Thank you, Kyle. I'll be in comments and I'll try to answer some questions.
Cool. See you in the comments. Awesome. Thank you again so much, Vikram. Up next, we have Jason Mays, who's a senior developer relations engineer for TensorFlow.js here at Google. And he's going to be talking about superpowers for next-gen web apps on machine learning. So take it away, Jason.
Cool. Hello, everyone. I'm Jason Mays, developer advocate for TensorFlow.js here at Google. And of course, I'm going to be talking to you about how to achieve superpowers in TensorFlow.js. So with that, let's get started. Now, before I get started, however, I know a lot of people in the chat today are very new to machine learning. So I want to make sure we're all on a level playing field and we all understand the basics. So often in this industry, we'll hear terms like artificial intelligence, machine learning, and deep learning. Now, what are the difference between those three things? So AI, or artificial intelligence, is essentially the science of making things smart, or more formally speaking, this is human intelligence exhibited by machines. But this is a very broad term, and in fact, we're in a realm of narrow AI right now. And all that means is that the machine learning system can do a few things or one thing as well or better than human counterparts could do, such as recognizing objects. For example, in the medical industry, people have been looking at brain tumors and using machine learning to classify those. And traditionally, humans might miss certain things in those images. They're very grainy images that come back from the medical scanners. And with the AI systems, we can now actually recognize those with higher accuracy and faster too. So that's a win for the patient and the doctor. And of course, machine learning, or ML for short, is essentially an approach to achieve AI that we just spoke about on the previous slide. And the idea here is to build programs that can find patterns in the sets of data that you present to it. And what's really cool about these systems is that they can be reused. And that's a very powerful thing here. So the same system that you choose to recognize cats can be used to recognize dogs just by passing it different training data. And if you look at the top right here, you can see how we used to do things for making a spam email filter in the old days. With traditional programming, we may have used conditional if statements. If the email contains a certain word, mark it as spam, and so on and so forth. Fast forward to today, and we now use machine learning to do the same thing, where everyone here is marking their emails as spam automatically, and then the machine learning will use statistics and mathematics to find out what words are more likely to be in spam emails in the first place, and then automatically mark it as such. And that means we can just retrain that every night, and the human doesn't have to maintain a list of if statements, which of course can take up a lot of time. And machine learning can be used in many other use cases as well. We've got computer vision, such as object detection. We've got numerical regression, which simply means for some input numerical value, can we predict some output numerical value? So if the square footage of a house is 1,000 square feet, then maybe we can predict the price to be $1 million in San Francisco, for example. And we've also got natural language, which is essentially the understanding of human language itself. So things like text toxicity that you saw in the previous presentation and sentiment analysis. Audio is also very popular these days, speech commands, that kind of stuff. If anyone's got a smartphone, then you're very familiar with the digital assistants on the smart devices these days, and that's powered by machine learning to make that all work. And then, of course, my personal favorite is generative stuff. So things like style transfer and creative examples. And you can see an example of this from NVIDIA on the right-hand side here. which is basically generating these faces. And the key thing to note here is none of these faces actually exist in real life. They've kind of been dreamt up. Just like I'd ask you to dream of a purple cat right now, you can probably do that. And here you can do the same thing, but with human faces instead, as it knows the essence of what a face actually is. Now, deep learning, or DL for short, is essentially a technique for implementing machine learning. You can think of this as one of the algorithms you can use in the program for the machine learning on the previous slide. And one such technique is a concept known as deep neural networks, or DNNs for short. And essentially, these are code structures that are arranged in layers that loosely mimic how we believe the human brain to work, essentially learning patterns of patterns, getting higher and higher level as you go up the chain. And we'll get more into that in just a little bit. So if there's one thing you take away from this summary here is that these concepts actually go back to the 1950s. These have been around for a long, long time, but it's only now that we've got the computing power at a cheap enough cost to make use of these algorithms. And you can see here how the deep learning is one such algorithm you can use to make the machine learning implementation work. And that machine learning implementation is trying to give us this grand illusion of artificial intelligence, which we're striving for longer term. Now, then the next question comes up, how do we train these systems, of course? And that's a very good question. And for this purpose, we're going to pretend to be farmers. I know we all got very different backgrounds, but we're just going to pretend to be farmers today. And we're going to try and recognize apples and oranges. And the first thing you need to do is find features or attributes that you can measure of the things you're trying to recognize. So in the case of an apples and oranges, you might choose weight and color, okay? And if you go back to your high school mathematics class, you might remember creating scatter plots like this. So if we have color on the x-axis and weight on the y-axis, and we kind of recorded hundreds of fruits, you might end up with a scatter plot something like this. You can see the green apples there in the green spectrum, and the red apples in the red spectrum. And then the oranges are slightly heavier in the weight axes because they're more juicy, more water, and they kind of fall slightly above there. Now, if we can draw a line to separate the apples from the oranges, we can then essentially predict what new data might be. If it falls above the line, we can say with some confidence that it's probably an orange. And if it falls below the line, it's probably an apple. And essentially, this is the essence of what's going on in machine learning programs, except instead of a human drawing the line, we're getting the computer to figure out the equation of this line for us. And that allows it to separate data so it can then classify it in the future with a high probability of being correct. And this is a very simplified view of that, but this is the essence of what's going on behind the scenes. However, if it was that easy, it would be done, but it isn't. So let's talk about why things can get harder. And of course, choosing correct features and attributes is very important. If we chose ripeness and number of seeds, you might get a scatter plot that looks something like this. And you can see here, there's no easy way to separate the apples from the oranges in this case. And you might be wondering, well, Jason, why would you choose such bad features and attributes? And sure, for apples and oranges, it might be obvious that ripeness and number of seeds is a bad thing to choose. However, what about those brain tumors we were talking about earlier in those medical scans? What features would you use for those? Things get very hard quite quickly when you're dealing with more abstract information that might be in the form of images or other data sets. And it doesn't stop there either. So far in our examples, we've just used 2 features and attributes. If we had to use 3 features in order to separate our data, so here you can see I'm using ripeness and number of seeds, and then I'm using the weight to kind of pull the oranges away so I can then put this kind of this rectangle or plane, if you will, between them to separate the data out. So now we're using a 3D graph and using a plane instead of a line, this rectangle and 3D space to separate the data. And it turns out that in machine learning, that 3D is not even enough. Typically using tens, hundreds, thousands, even millions of dimensions. And our human brains can't visualize this very easily. However, the mathematics is actually the same. And instead of using a plane like we see here, we're using something called a hyperplane, which simply means 1 dimension less than the number of dimensions that you actually have. So you can see here how we've got a 2D rectangle separating the 3D space. So it's 1 dimension less than the number of dimensions that we have, okay? And that's a principle that's going on here when we're separating data at higher dimensions as well. So it should be easy, right? We've got dogs, we've got mops. What could possibly go wrong? Well, essentially, some dogs look like mops, as you can see here. And even as a human, I struggle to tell the difference at a quick glance. Now, the reason I bring this up is that one of the biggest challenges when creating an ML system is finding enough unbiased training data to recognize the object that you're trying to recognize in all the different environments it might be in. So if you're trying to recognize cats, for example, you might need 10,000 images of cats of different breeds, different fur colors, different fur patterns, different stages of life cycle, like kitten versus adult cat, and even in different environments, indoors, outdoors, different lighting conditions, different rotations. All this stuff is required to have the best chance of understanding what cat pixels really consist of. Now, the other thing to point out here is that data is not always imagery. It could be tables of data. It could be sensor recordings, sound samples, and much, much more. Obviously, in the slides, I use visual examples as it's nice and easy to see, but just bear in mind it could be other stuff as well. So now we come to why do we want to do machine learning in JavaScript? And that's a good question as well. And as you saw in the previous presentation, we can run in all of these environments: browser, server-side, desktop, mobile, and Internet of Things. But if we dive into each one of these environments further, you can see many of the technologies you know and love and maybe even using already. We've got the common web browsers on the left-hand side there, Node.js for server-side, React Native for mobile native applications, and Electron for desktop native applications. And we can even run on the Raspberry Pi via Node.js if you wish to do so for Internet of Things. And JavaScript is one of the only languages out there that can run across all of these platforms without additional plugins and so on and so forth. So it's very powerful for that reason alone to use JavaScript. However, with TensorFlow.js, you can retrain via transfer learning or write your own machine learning models completely from scratch, just like you might be doing already in Python, but of course in JavaScript. And with that, you can make anything you might dream up, from augmented reality, sound recognition, sentiment analysis, conversational AI, and much, much more. In fact, we're going to see a few more examples today. Now, there's several ways you can use TensorFlow.js, depending on your familiarity with JavaScript or machine learning, or both. And the first way, the easiest way, is to use our pre-trained models. These are really easy to use JavaScript classes for many common use cases. And you can see just a few of our offerings here on this slide, things like object detection, body segmentation, pose estimation, and we can even understand the human face and hand pose estimations, along with BERT, which is a natural language processing model, which can understand language as well, which is very, very powerful. And you can see more of these models on tensorflow.org/js/models if you want to see all the others that we have available as well. Now, I'm going to go into a few of these today just to give you a feel for how they work. And the first one I want to show you is object recognition. This is using a model known as Coco SSD behind the scenes, and it's been trained on 90 object classes. And that means it can recognize 90 things out of the box, such as these dogs on the right-hand side here. And what's really cool is that because this is object recognition and not image classification, we can actually get the bounding box information back as well to show where in the image the dogs are. And that also allows us to then count how many dogs there are too. So image recognition would just tell you that there are dogs in the image, but not where or how many. And that's the difference between image recognition versus object recognition. So let's switch over to a demo to kind of see this in action. So if I bring up my web page here, this is just a glitch demo that I created, vanilla JavaScript, HTML, and CSS going on here. And I've got some images. And if I click on them, you can see I can get real-time classifications of the objects contained within them as I click. And you can see here how easy it would be to make a smart webcam or something like this to classify if your dog is going near the treats in your kitchen and send yourself an alert. It wouldn't be very hard to do that using an object detection model like this. But of course, we can go further than that. We can enable our webcam, and you can now see me actually being classified in real time as I speak to you here today. Now, of course, it detects me as a person, and it thinks this big black frame behind me is a TV because it wasn't trained on paintings. Of course, it probably looks like a TV as far as it's concerned, and that's completely fine. To get higher accuracy on other objects, you need more training data to then learn that this is actually a painting versus a TV. Now, the real cool thing about this is that this is running completely in the web browser in JavaScript, and that means my privacy is completely preserved. None of the imagery is being sent to a server for classification. It's all happening in real time in JavaScript on the front end. And in today's world, where privacy is top of mind, that is a really key thing. And with TensorFlow.js, you essentially get that for free, which is kind of neat. Now, going back to the slides, one moment. Whoop, there we go. The next one I want to talk about is face mesh. Face mesh is just 3 megabytes in size, and it can recognize 468 facial landmarks on the human face, as you can see in the animation on the left-hand side. Now, we're starting to see people use this in really interesting business use cases too. On the right-hand side here, Modiface, who's part of a L'Oreal group, have used face mesh combined with WebGL shaders to color in this lady's lips in real time so she can try on different lipsticks without even leaving her house. And you can see how realistic that looks. It looks like it really belongs there on the lips. It's not kind of this kind of patchy effect. It's really well aligned, and it works in real time in the web browser. So I just want to show you a demo of face mesh in action as well. So if I bring back over my web browser here, I'm just make it a little bit larger for you. One moment. There we go. So you can see here on the left, face mesh in action. It's recognizing my face as we anticipated. And even better, because this is JavaScript, not only am I doing the machine learning detection on the left-hand side here, I'm also able to render a 3D point cloud of my face on the right using 3.js. And JavaScript is really powerful at data visualization, 3D graphics, 2D graphics, and much, much more. From day one, it's been all about the presentation of information. So it's got very rich libraries to bring these ML models to life, as you can see in this demo. And right now, even though I'm presenting to you, you can see I'm getting quite a high frames per second in the high 20s there. And of course, that would be higher if I wasn't sharing my screen and using my GPU to do all of that. However, some of you may have noticed at the top right here, we can actually change the execution environment. So if I don't want to run on the GPU, maybe I want to use the GPU for some game graphics or something, I can actually force the machine learning model to run on the WebAssembly. I can change that over right now, and you can now see we've got a slight drop in performance, but it still runs very fast, even on the CPU as well, using WebAssembly. And for the keen-eyed view there, you can also see there's also a CPU version available, which is simply executing in plain old JavaScript without any fancy acceleration using WebAssembly. And that is the slowest of all three. I'm not going to do that right now, but that would drop the speed even further. But is another execution path for lighter weight models if you choose to do so. Now, going back to the slides, let's see what else we've got in store today. So we've also got body segmentation, and this allows you to distinguish 24 body areas across multiple bodies all in real time. You can see this happening on the right-hand side there in the imagery. And what's cool is not only can you distinguish the different body parts, but we've also got the pose estimation coming back that you can see with the blue lines contained within those three bodies, which is very useful for gesture recognition or that kind of stuff. We've already seen people from the community make some amazing demos to do with fitness or healthcare, which allow them to count the reps they're doing for their fitness workout or yoga pose estimation, and so on and so forth. And with a little bit of creativity, we can essentially emulate the superpowers that we were promised by the movies right now with a little bit of digital creativity. So here's a few examples I've created, and also from the community as well. The first one I made in just one day of coding, and it allows me to become invisible in real time. It's kind of like an invisibility cloak. And the key thing to note here is to watch as I get on the bed. You can see that the bed still deforms, even though that I'm removed completely from the frame on the right-hand side there. And it gives you this kind of ghostly Harry Potter-like effect, if you will. And it's not perfect. You see my arm coming out every once in a while there. But for one day of coding, that's not bad as a proof of concept to kind of get an idea coming to life. And of course, you could spend a lot more time refining the model to make it work better for your situation. But this was using body pics. And of course, if I know where my body is, I also know where it is not. And that allows me to update just the pixels where I am not in order to get this effect working. And this is available on GitHub for those of you who want to try it live after the show. Here's one from our community who's used TensorFlow.js combined with WebGL shaders to create this kind of superhero style effect where he's shooting lasers from his eyes and mouth. This is a fun example. It could be used for some creative activation with a movie company to kind of maybe tease their new upcoming superhero movie or something like this. You can see how this could be quite fun. And it runs in real time, buttery smooth in the web browser, as you see right now. So do you think about combining machine learning with existing web technologies as well? And just to kind of emphasize this, I also made this teleportation demo that when I'm using WebRTC, which is web real-time communication, combined with 3.js and Mozilla's A-Frame, which is essentially WebXR, mixed reality in the web browser, I can now segment myself from my bedroom in real time, transmit just for segmentation, as you see in step 2, which is great because I save bandwidth as well. And then I can place that segmentation somewhere else in the world on someone else's mobile device. And in the future, of course, maybe we'll have something like Google Glass where you can actually just see my projection rather than having to hold a mobile phone up. And maybe in future presentations, that's how I'll be talking to you. That'd be kind of cool to give you a more personal experience as if I'm really there. And of course, you can add spatial audio that's supported in JavaScript as well to hear me from the correct area in your house at the same time. And there's other delightful creations you can make too. Here's another one I created to solve a problem that I have in my life. I don't know about you, but I really struggle to know what clothing size I am. And I made this to basically solve this problem on a website. So at point of checkout, I can understand if I need to get a small, medium, or large, and it can select automatically for me what piece of clothing I need. I just enter my height in centimeters. I then stand once to the front and once to the side. And within 15 seconds, I can then get an estimation of my clothing size. And that's great for me because I can spend less time trying to think about these things. And it's great for the company because they spend less money with returns. And it's a win-win situation for both people there. Or you can combine with other web technologies, as I spoke before. Here's another WebXR example from someone in the community. You can see here how he can take a magazine, he can extract the person from the magazine and bring them into his living room with his cool 3D particulate effect using 3.js. And this is actually running on a 2 or 3-year-old Android tablet, I believe. So you're getting great performance with all the 3D graphics and things, even on these older devices too. So what about transfer learning? This is the second way you can kind of build models with TensorFlow.js. And you've seen some of these examples in the previous presentation, such as Teachable machine. But essentially, this allows you to retrain existing models to work with your own data. And of course, this is very important when you try to push the boundaries here and work with your own data sets. And Teachable machine, as was mentioned before, I'm not going to show you the demo for this one because it was already shown. But basically, you can, for 3 common models, namely object detection, sound recognition, and pose estimation, you can train models to recognize those things very easily in the web browser using a very simple interface. And you can then export those models and save them to your own website or web hosting service to then use with whatever situation you might want. I've seen people use this kind of stuff to control Raspberry Pis to open the garage doors when it's dark outside, or sorry, other way around, close the garage doors when it's dark outside automatically for them, that kind of stuff. So you can imagine how you can combine it with other technologies to make some really powerful systems. Now, if you want to go a little further and have production quality systems, then we recommend using Cloud AutoML. And this can be very good for computer vision problems, as you see here. So what's happened is someone's got gigabytes of training data for different types of flowers. They're trying to recognize different types of flowers. So they've uploaded that to Google Cloud Storage, and then they've imported it to Cloud AutoML, as you see in this slide. You can then choose if you want to train for higher accuracy or faster prediction times. And that's up to you, depending what you want or how fast you want the model to work. That's up to you. You can set a budget or train for several hours or maybe a few days, and then come back to you with the best model it found that fits that criteria. And then, of course, you can export to TensorFlow.js is one of the options there, which allows you to download the model.json files, which you can then use to run in the web browser. And you might be wondering, well, how hard is it to take this production quality model and use it in the web browser? And the answer is it's so simple, it fits on a single slide. So let me just walk you through what's going on here. Essentially, at the top here, we have 2 imports. The first one is TensorFlow.js, and the second one is the AutoML library. And then down below here, we've got an image tag. This is just some HTML image, just a daisy.jpg in this case, but we want to classify. This is a new image the machine learning model has not seen before. And then here down below is the 3 lines of code we actually want to execute. So we've got this asynchronous function called run, and we're using await.tf, the AutoML.load image classification, and we simply pass to it the model.json file we downloaded on the previous slide. So that will be hosted somewhere on a content delivery network, or maybe hosted on your web server somewhere for it to load. And because this might be a few megabytes in size, this is an asynchronous operation. So we're going to use the await keyword in JavaScript to wait for that to finish loading before we continue our code execution. So on the next line, once the model has loaded, we can now grab a reference to the image we want to classify. So use document.getElementById and pass to it the ID of Daisy, which is just grabbing this Daisy image above right now. And that's assigned to the constant called image. And then on the third line, we simply use await model.classify and pass to it the image we want to classify, which in this case is our constant above. And again, because this might take a few milliseconds to execute, we have to use the await keyword here because that's technically an asynchronous operation. And then we get a JSON object returned to our predictions constant, which then has the classifications that is found for that given image. And with that, you can then do anything you like. With that information, you can then tell a robot to move, or you can activate something, alert yourself via WebSockets to something being detected in a room, or whatever it is you're trying to do with your application. It's up to you as a JavaScript developer to then do something useful with that information. And then the third way to use TensorFlow.js, of course, is to write your own code. And of course, writing this from scratch is beyond this very short presentation today, but we're going to focus on the superpowers and performance benefits you can get by writing your own code in TensorFlow.js. Now, as you saw somewhat in the previous presentation, we've got a couple of APIs you can use here. And essentially, we've got two. One is a high-level layers API, which is very similar to Keras that some of the Python folk might be already familiar with. And then the second one is the lower-level ops API, which is more mathematical, that allows you to change like the linear algebra that's going on behind the scenes to tweak things and make new high-level things should you wish. And essentially, this comes together as shown. You've got the pre-made models on top there. They sit upon the layers API, which itself sits upon the core or ops API. And then these understand how to talk to different environments, such as the client side. And by client side, I mean things like the web browser. And then the client side environments understand how to talk to different backends. And we kind of touched on this in the previous demo, where we've got 3 different backends we can execute on there in the client side. We've got the CPU, which is the slowest form of execution, just plain old vanilla JavaScript. We've got WebGL, which is the graphics card to get high performance on the graphics card. And we've got WebAssembly, or WASM for short, which gives you high performance on the CPU, which is especially important for mobile devices that don't have very good graphics cards. You can often squeeze more performance out of the WebAssembly implementation on those for smaller models. And by smaller models, I mean things under 5 megabytes in size. And then the flip side is also true for the server side. You can see here we've got Node.js, and on Node.js, we've got the same actual bindings to C++ as Python does to TF-CPU and TF-GPU. And what that means is that you've got the same AVX support for the CPU and the same CUDA acceleration on the GPU as you get in Python, but within Node.js. So for JS devs, that's a great win because it allows you to stick to JavaScript, but you get the same performance or better, as we'll see on the next slide, in Node.js. And of course, some of you might be wondering, well, I really want to stick to using Python for my machine learning generation, but then I want to use that resulting model in Node or in the browser. And yes, that is possible too. In fact, if you choose to use Node.js, you can use a Keras model or a TensorFlow saved model without any conversion. You can just run that in Node.js completely without any conversion, and it runs just as fast or faster as I spoke about in the previous section. And if you want to run in the client side, then you need to use our TensorFlow.js converter. And there's actually a code lab available for that right now on codelabs.google.com. If you type in TensorFlow.js on there, you'll find the Python to TensorFlow.js code lab, which I highly recommend you check out if you're interested in that. And that will convert the TensorFlow saved model format to the model.json format that we need to run in the web browser. And that's only required if you're running in the web browser. As I said, server side does not need any conversion for Node. So let's talk about performance then. Here is MobileNet V2, and you can see here on the graphics card, TensorFlow Python takes 7.98 milliseconds, and TensorFlow Node takes 8.81. So that's less than 1 millisecond of difference for inference times, which is within margin of error for the server, depending what it was doing when we're taking these recordings. And the key thing here is that if you have a lot of pre or post-processing, and for those of you new to machine learning, pre-processing is what you need to do to your input data to get it into a form that the machine learning model can digest. And often, if you take something like an image, you might need to resize it. You might need to convert the numbers to be a grayscale image, or then normalize them between 0 and 1, all that kind of pre-processing steps. And if you convert that pre and post-processing to be in Node.js, you can actually get significant performance boost over Python. And you can see here a case study with Hugging Face, who converted their Distilbert implementation for their model to Node, and it got a 2 times performance boost just by doing that. So that's a pretty cool win just by converting some of your pre and processing code to Node. So the inference time is roughly the same as we saw, but the full end-to-end classification time, including the pre and post-processing, actually ended up being 2 times faster. And that's due to the just-in-time compiler of JavaScript that's unique to JavaScript that compiles at runtime and optimizes things at runtime that allows it to get that performance boost. And then we're going to wrap up here with 5 superpowers that you can get on the client side, but essentially harder or impossible to achieve on the server side. The first one is privacy. Because you're executing completely in the web browser in this use case, none of the data is sent to a server for classification. So the user's privacy is then preserved. And that's really useful for medical applications or legal applications, or maybe even you're living in a country we have very strict privacy rules, like over in Europe with the GDPR stuff. Second point, lower latency. Because you're not sending the data to the server and back again, you don't have that round trip time for classification. So things can execute much faster being on device. The third point, lower costs. Because there's no server involved, you don't have to spend tens of thousands of dollars for a popular site to hold all those machines with high memory and high GPUs and high CPUs to do the inference for all of your users. Instead, you can have it all running on device. The fourth point, interactivity. JavaScript from day one has been designed for the presentation and display of information. And therefore, we have very rich libraries that are far more mature than other languages to display that information, as you saw with our free.js demos earlier on. It's very easy to make these very powerful things come to life in a matter of days rather than weeks. And then the fifth point here is reach and scale. Anyone in the world can click on a link and run a TensorFlow.js model, even if they have no machine learning experience. They can experience it and try it out in the web browser. The same is not true if you're trying to run in Node.js or Python on the backend, because you have to install TensorFlow, you need to understand Linux, you need to clone the GitHub repository, you have to read the README and hope you understand the instructions to know how to use their code. And then if all of that works out, you might have a chance of running the model on the back end. So you can see you can have a larger reach and scale for your models that you produce and allow people to try this out, tens of thousands of people instead of just a few hundred. And then if we go to the server side here, we can also see there's some benefits of running on the server side as well. We can use the TensorFlow saved model without any kind of conversion, which is also very useful at certain times. And that allows us to run larger models that maybe you don't want to push to the client side. Maybe they're gigabytes in size. It probably wouldn't be wise to wait for many minutes for the model to be pushed down to a little mobile device. That's probably not very efficient. The third point, it allows you to code in one language. If you're already using JavaScript, and currently 67% of professional developers out there use JavaScript according to the Stack Overflow survey of 2020, but it allows you to keep all your code in one language, which is very, very powerful. Allows you to reuse your code and have better maintainability. And then the fourth point there is the performance benefits, as we saw before. You got the same C bindings as TensorFlow Python, but we get the just-in-time compiler boost for pre and post processing, which allows you to optimize your code at runtime, which, as you saw for Distilbert, can lead to a 2x performance boost. So I'm going to wrap up the talk with resources to get started. And if there's one side you want to bookmark, then this one is the one. Essentially, we have our website, TensorFlow.org/js, to get more resources there. All of the models that I've spoken about today are on our models page, but there's many more available too. I've only gone through 3 of them today. There's many, many others on our models page, which you can see on the link on the slide. We are open source, so that means we're on GitHub as well, and we welcome pull requests if you want to contribute to the project. And we've even got some boilerplate code on CodePen and Glitch. So if you're new to JavaScript even, I can show you how to use the webcam with our models in a very easy 30, 40 lines of code, and you can be up and running very quickly. You can just clone those repositories and start tinkering with them. We've also got a book called Deep Learning with JavaScript. That's pretty decent. But I also know that Grant Laborde is in the live chat right now as well. And he's producing a book with O'Reilly that I've been technically reviewing. And it is awesome. So I do look out for that one as well, which will be coming out shortly with O'Reilly. And with that, my only ask here is to come join our community. I can't put all of the demos on one slide or even a whole presentation. There's new ones coming out every single week. But if you check out the Made with TF.js hashtag on Twitter or LinkedIn, you'll find a ton of inspiration to get your brains excited. And if you do make something, do tag us, because that means you might be featured on our future show and tell events that happen every quarter on YouTube, where I get people in to talk about the amazing projects they've created, and maybe even a blog post on the TensorFlow blog too. So do check that out. And I'll just leave you with this final piece of inspiration here. This is a guy from Tokyo in Japan. He's actually a dancer by day, but he's used TensorFlow.js to create this really cool hip hop video, as you can see on the slide. And my reason for showing you this is that machine learning really now is for everybody. It's not just for engineers and academics, but creatives, musicians, and artists can now start to tinker with machine learning too. And I'm really excited to see how TensorFlow.js can enable these people to take their first steps as well. So do use that hashtag if you make something cool with it. And on that note, please feel free to keep in touch with me as well. I'm Jason_Mays on Twitter, and I'm Creative Tech on LinkedIn. So do keep in touch, and I'll take any questions you might have right now as well. Thank you.
Awesome. Thank you so much, Jason. That was a great presentation and a lot of fun demos. There were a lot of comments about how can they test along with you and play with these demos.
Yeah.
So essentially, TensorFlow.org is where they can find those models.
TensorFlow.org/JS.
Slash
So
JS.
yes,
Okay.
TensorFlow.org would be the Python version, but /JS is the JavaScript version. So that is the place to go. We've got a lot of the demos up there, but also check out the hashtag made with TF.js on Twitter and LinkedIn, because there's far more available from the community that are coming out every week, but are really, really interesting to see too. We've had people do some amazing things like depth estimation and people converting some interesting Python models to JavaScript, or face masks, and some really amazing stuff to check out over there.
Awesome. Very cool. And then a couple questions from the audience here. We have this one from Rohan, looking to build a front end with React and do some deep learning with TensorFlow.js. So what would you recommend there?
Yeah, so obviously, TensorFlow.js is just a library that you can use on the front end, just like you might import jQuery, you can import TensorFlow.js. So the way you change, you don't need to change how you create your front end applications. You can continue to use React or whatever frameworks you're already using, and then use TensorFlow.js to basically execute the machine learning models. And then when you get the results from that, you can pipe that into your React framework or whatever it is you want. So no need to change what you're doing already on the front end there.
Gotcha. And I know this talk really covered TensorFlow.js, but this did come up in the chat a couple times. What is the state of Swift for TensorFlow?
Yeah, I do not know anything about that, I'm afraid. I only cover the JavaScript side. We need to find a Swift developer advocate to talk about that one.
Gotcha. Yeah, I figured as much as well, but I know this popped up a couple times, so wanted to help make sure the audience had something there. Let's see. And then there was, oh, wow. Let me scroll back over to here really quick.
Maybe towards the end.
Yes. So I know you shared a lot of positive positive tips and tricks and resources and stuff like that. What is just a word of advice for acknowledging that many of the viewers currently are new to machine learning and thusly new to TensorFlow? So where do you recommend is the best place to get started?
Yeah, that's a great question. I highly recommend, as you've seen in the two presentations today, like just try out Teachable Machine as a very first starting point. Feel that rush of adrenaline when you actually recognize an object for the first time, and that will get you super excited. But then try and think about how you can use that in ways that are not as obvious as just recognizing an object. If you can recognize an object, you can also count objects, and so on and so forth. So try and think how you can push that further to then do something useful in your life. Think about a problem you might have in your life that you might be able to solve using this new ability that you've now gained. And then once you tried out Teachable Machine, check out our pre-made models. All of our pre-made models have very easy to use code snippets. If you're very basic level JavaScript engineering, that's completely fine. As long as you know how to import stuff and call a function, you can basically use our pre-made models. And I'd encourage you to just try some of those out, see the data that comes back, get familiar with the types of data that come back in the JSON format, and try and use that to do something useful. As I mentioned, people have managed to open and close garage doors, feed their pets, or whatever it might be. Like it's completely up to you. And yeah, get creative. The hardest thing is to start a project. Once you've started, it's just a case of iterating on it thereafter. And as you get more confident, you can then start to dive deeper into the lower level workings. As you saw in the presentation, we've got these lower level APIs you can use to make your own ML models from scratch. And you don't have to do that on day one. In fact, 90% of people will take an existing model and use that to make their idea come to life. And it's very, very few people actually need to make an ML model from scratch typically. So don't worry about that. Just focus on making the thing you want, and then you can go deeper as you need to optimize it and so on and so forth. Yeah.
Awesome. We do have another question here from Ryan. You mentioned the size of the model in terms of megabytes. How does the model size directly correlate to the computational requirements of the machine when deployed?
Yep, that's a great question. And obviously, model sizes vary completely in TensorFlow.js, depending how many neurons and things you're using in your architecture. And they can vary from kilobytes to megabytes, as we just said. So essentially, larger models means that it has many more operations that it's probably executing within the model. And that just means it's going to take more time to do so, because you can think of each operation as some mathematical calculation, if you will. So if you've got more of those, then it's going to take a longer time to execute. So generally speaking, the larger models tend to execute faster on our WebGL stack because we can parallelize those executions using the GPU, which is designed for parallel execution, versus on the processor, which is more sequential execution. So the smaller models tend to work very well on the CPU using WebAssembly, and the larger models tend to execute faster on the GPU, which we can then start to parallelize some of those model executions.
Gotcha. Awesome. We did have, so as mentioned at the beginning, we did have a lot of questions from the audience during their registration, stuff like that. This is one that is fun to challenge our speakers with. What is the most challenging project you've worked on?
Oh my gosh. Again, like the previous presenter, I think probably the most challenging one is probably confidential. I'm not allowed to but I think in terms of my machine learning projects that are public, there's been situations where I've been trying to do a custom thing and I didn't have the training data for it. And maybe there wasn't a training data available from Kaggle or something just to take and use. And I'd have to try and make my own data set. So there's one example that I was trying to create using Lego bricks. And I wanted to be able to allow children to create houses or something with Lego bricks. And then using a GAN, I can bring it to life as a photorealistic image to kind of visualize what the child was making with Lego bricks. And of course, there's no data set out there that has a bunch of houses that are Lego bricks to image conversions. So I'd have to build 1,000 houses myself to make that data set. And I figured the best way to do that was actually to hire an external company to help me generate that training data in the end. But these things do pop up from time to time, and I think that getting enough training data is often the biggest struggle in many ML problems, and then refining that to then work well with your model architecture.
Awesome. I know we did have a lot of comments similar to this one as well, that your talk has inspired and given them a lot of ideas for projects already. So as you were talking about, the hardest part is getting started. And so how would you recommend, as Khaled here says, he's got 2 ideas. How do I settle on which one to start with? Yeah.
I mean, whatever you're more passionate about, just go with your gut instinct there, I guess. Whatever's fun for you, because if you're new to machine learning, you've got to keep it fun as well. You've got to have some fun whilst making these things, and you start to break that problem into smaller parts. Like what components does it probably need? What machine learning model can help you achieve that? So if you're trying to recognize cats, then maybe our Coco SSD model is the one to go for because it already recognizes cats, and you can very quickly get something working. If you're trying to do something like speech recognition or something, then check out our audio recognition model for short form audio that's available on our models repo as well. So basically good starting points to make something that illustrates the thing you're trying to do, and then you just keep diving deeper within that as you go further down the rabbit hole that is machine learning. And of course, as I mentioned, there's 2 great books. There's the Machine Learning in JavaScript by Manning, that it was written by our team. It's aimed at beginners, but it can get a little bit technical in some parts. And then there's Gartner Board's book, which is from O'Reilly, that's coming out very shortly, that I believe could be very, very good for beginners. It's very down-to-earth book, and it explains things with no technical or ML background required. So do check out that book as well.
Definitely, and excited to have him on the TensorFlow Everywhere event later on today.
Oh, awesome, good stuff.
He'll be speaking later today. He's also being very helpful in the chat as well. There was also a fun back and forth dogs versus cats during your presentation as well. Just quickly, what is, in your opinion, the most exciting niche in the deep learning space?
So obviously this is my own personal bias, but I'm really excited by all the generative networks that are happening right now, all the GANs. I think that's very, from a creative perspective, very, very interesting to me, both for voice and for imagery and video and all these other things that exist. I think that's a very interesting space creatively to be experimenting in. These things are going to get better and better with time. So at the moment, we can't really do it in real time, but another decade maybe, and our computer processing power will catch up, and the model architectures will be even more efficient. And once we can do that in real time, I'd be very interested to kind of do that kind of stuff. To have a digital version of JSON or something that can just exist on the website, you can talk to me there, I can combine that with some natural language processing and have a fun time with all of that. So yeah, we're going in the right directions, but it will take a few more years to get there. So yeah, I'm excited about those areas, personally speaking. Yeah.
So, well, thank you again so much for taking the time out of your Saturday to join us. It was great having you here. I know I learned a lot, and it sounds like there was, a lot of ideas sparked and everything like that in the chat. So hopefully you can stick around and maybe answer a couple more questions in the chat.
Yeah, and if anyone makes anything, please use that hashtag made with TF.js so I can find it on Twitter and LinkedIn, and share it, give you some love on my social media as well. It's always good to spread the love. So do tag me in anything you make.
Perfect. Thank you again so much, Jason. It was great having you here. And don't forget to give Jason some feedback on our survey, TFOR-survey 2.
Perfect.
Thanks,
Thank you very much.
Thanks, Jason. Cheers. Awesome. Thank you again, Jason. It was great having you. A lot of awesome stuff. Up next, you'll recognize our speaker from yesterday as well. Happy to bring back to the stage Lawrence Maroney, who is a Google developer advocate with TensorFlow. And he'll be taking us through zero to hero with TensorFlow. So over to you, Lawrence.
Thank you so much. And Jason's always a hard act to follow, but I'll do my best. So I'm Lawrence. I lead the AI advocacy team at Google AI around machine learning and AI and those kind of things. And, let's just roll our sleeves and get down to it. And let's take a look at, how machine learning works on a fundamental level and how you can start coding for it. And we'll go through a simple example where we use image classification. All right, so I always like to start with thinking about what about coders and what's machine learning like for the average coder. So let's take a step back and say, well, what is our job? What is it that we do when we actually write code? And I always like to look at it as we express, we want to solve a problem. And we do that by having rules that we express, and those rules act on data, and then they provide us with some kind of answers. So for example, if you work in financial services, you're probably familiar with a PE ratio for stock, which is just price divided by earnings. And it's a good way of establishing, a very basic way of establishing the quality of a stock. And the code might look a little bit like this. You're going to pull the data out of earnings, you're going to look at the current price, and you're going to return one divided by the other. It's very, very simple. Or for example, if you're creating a game, like a breakout game like this one, you have your rules, you have your data, and they provide the answers. So for example, the data might be the location of the bricks, the location of the ball, the trajectory of the ball. And you write a rule to say, hey, look, when the ball collides with a brick, you want to remove that brick and then change the trajectory of the ball. And as a result, you're writing rules that act on data to kind of provide answers. So I like to look at traditional programming like that. Let's think about it at a very simple diagram like this, where rules act on data and provide answers. And this is what we as developers, have been making our bread and butter on since the dawn of the industry. And where machine learning comes into it is to fundamentally rethink this diagram a little bit, where we flip it around. So instead of rules and data in with answers out, let's have answers and data in with rules out. So what does that mean? Well, the idea behind this one is that there are some algorithms where the rules for you to kind of create and write those rules yourself are just too complicated. So for example, if you wanted to look at what the contents of an image, like in computer vision, how would you do that with a lot of if-then kind of rules? You might be able to do it, but you'd have many thousands of rules, even for a very simple scenario. So the idea behind machine learning is, well, what if we can kind of give the answers and the data to a computer to say something like, hey, this is a cat, this is a dog, this is a cat, this is a dog, and then have the machine figure out what it is about the answers and data that you're putting in that distinguishes one from the other, and then use that to establish what the rules are. And that's really what machine learning is. So another example, if we talk about activity recognition. So say you're building a device like an Apple Watch or something like that that you want to use to help people with their fitness, and you want to be able to recognize the activity that they're doing. Well, think about this from the rules perspective. If you're doing something like saying, hey, it has an accelerometer or has something on it that can detect the speed that the person's going at, you could say, hey, if the speed's less than a certain value, we can say that that person's walking. And then we want to detect running, we'll say, well, if it's less than a value, we'll say that they're walking, otherwise they're probably running. And then if we want to add biking to that, yeah, we can still do it. It's a rough algorithm. We can say if the speed's less than a certain amount, they're walking. If it's less than a higher amount, then they're running. And if it's greater than that, otherwise they're probably biking. It's a crude algorithm. It kind of works. It's not great, but we could see where it would work. But then what about an activity that isn't as easy to detect, like golfing? I mean, how would we do that? How would we be able to write an algorithm to do that? So if we go back to this diagram and we say, hey, look, it's answers and data in machine learning space, and then rules come out of it, then we could do something like this and say, well, okay, here's all the data that I've gathered on the device about the person's activity, and I know they were walking when they were doing that. I knew that they were running with this data, biking with this data, and golfing with this data. And let's start spotting patterns in that data. And we say, hey, look, these two things are always 1, 0, 0, 1 when they're walking. And this one's always 1, 1, 1, 1 when they're running. And this one's 1, 0, 1, 1 when they're biking. And the computer's able to determine this pattern. And then if that is a consistent thing, now it's established a whole new set of rules to be able to determine if a person's walking, running, biking, or golfing, just based purely on the data. And it may not be the kind of if-then rules that we can rationalize, like, hey, if the speed was this much, and it can be something far more subtle, but it's there. And that's ultimately what machine learning is all about. It's finding those patterns in the data that match particular labels so that the computer can figure out the rules. Now, a computer isn't smart enough to do this, and that's why machine learning is able to come into it. So the way the machine learning paradigm works is like, say, going back to this, like looking at, hey, we can see these patterns always exist and are distinct for these labels. So then we can say, okay, we got a pile of data and we got a pile of labels. Let's make a guess. Let's make a guess that this piece of data matches this label and this piece of data matches this label. And that rough guess will give us an estimation for, the beginning of whether this is going to work or not. So for example, if you're building something that is like determining the difference between a cat and a dog in an image, you'd make that guess, and you'd expect that guess to be right 50% of the time, right? Because it's a coin flip and it's either a cat or a dog. There's only two classes. Or if it was determining rock, paper, or scissors images, then it would be right 1/3 of the time, because it's there's 3 different classes, and a random guess is going to get it right 1/3 of the time. But let's start by making that guess. And then measure that accuracy. 1 out of 2 if it's cats or dogs, 1 out of 3 if it's rock, paper, scissors. If we're detecting 4 activities, like I was showing earlier on, it's going to be 1 out of 4. But we've made our guess and we've measured our accuracy. Now with the data that we have from that, you can optimize your guess. You can say, okay, let me look at how I guessed. Let me look at where it went wrong. Let me look at these places where it was good. Look at these places where it was bad. And then repeat. And then the logic being that your next guess is going to be a little bit better when you measure your accuracy. So when you optimize that, that's going to be a little bit better. And continually, those guesses get better and better and better until you reach a point where you've now built something called a model, and that model has figured out the pattern match between the input data and the labels. So then at runtime in the future, you're going to be able to give it new data, and it can kind of make that sort of guess. So that's what we have here. So we're feeding in labels and data. Machine learning is that loop that I showed you is just like establishing the pattern between those labels and the data to infer a bunch of rules. So then at runtime, you can pass data into it, like you can pass it a picture, and then it will apply the rules that it has learned to that picture and say, I think this is a cat, I think this is a dog, I think this person is walking, those kind of things. I think it's a rock rather than a paper or scissors. And that's ultimately what machine learning is all about. It's actually pretty straightforward and pretty simple. But what I just showed is very high level, and let's dig down a little bit deeper into that to think about computer vision. Now, computer vision would be the same kind of problem that we were talking about earlier on, where it's like, how can we see pixels within an image? How can we determine them? Think about all those if-then rules. So how would that work? So I like to simulate that by saying, okay, when you show an image to a computer, it doesn't know what that image is of. There's no context for the computer to understand the contents of the image. And I simulate that by blurring the image so that this image is of something in particular, but I've blurred it. So if you're familiar with things like Instagram or Photoshop, they have filters that you can apply to an image to do things like sharpen the image or maybe add effects. But another thing that filters can do to an image is extract features from that image. That when you apply a filter to an image, everything but the feature that filter can extract will fade away, and just that feature would be shown. So for example, say there was a filter that I could apply to this image, that everything else would fade away, but then I would just consistently see these two kind of vertical cylinders. And then you go, well, as a human, you're probably looking at that and saying, aha, I see legs. right? So computer doesn't see that, but it will see this pattern consistently there. And maybe there's another filter that in images that the computer would consistently see these things being extracted by the filter. And maybe there's another one that the computer would see this thing being consistently extracted by the filter. So again, you and I are looking at this. We saw legs, we saw hands, we saw a face. So we can kind of now begin to see that this is an image of a person despite the blurriness. But the computer hasn't done that. But the computer has done is say, hey, that filter gave me something, that filter gave me something, and that filter gave me something. And when the human, who's creating this system for me said, when those three things like were present, that's a human. Now the computer can start putting together an algorithm of pattern matching to say, well, when I apply these three sets of filters and I start getting results from that, that's going to be a human. Because when I did that on my test data that was labeled as humans, that was the result that I got. And then similarly, maybe there's another three filters that you could apply to an image. Say, hey, when I see something like look like this, and something that looks like this, and something that looks like this, the training data that I was given said, well, when those images were all horses, and now the computer is beginning to establish this set of rules, where it's saying the filter that gives me the three filters that give me the results at the top, were consistently giving me results when the image was labeled human. The three at the bottom were consistently giving me results when it was labeled horse. And now the computer is able to establish the difference between a horse and a human in images. And this is the basis of computer vision. So you'll generally train models in computer vision by giving a whole bunch of samples that are labeled. In this case, there's only two. But think about, for example, maybe for medical needs, you could have like chest X-rays, and there's 10 different diagnoses on a chest X-ray, and the same kind of thing would happen, where it's like, okay, here's a bunch of chest X-rays where someone's healthy. Here's a bunch of chest X-rays where somebody has disease 1. Here's a bunch of chest X-rays where somebody has disease 2, and then the computer is able to figure out the filters that it applies to the image that consistently match to those diseases, and now you suddenly have an image classifier that can recognize diseases in X-rays. Same concept, exactly the same thing as we're doing here with humans and horses. What does this look like in code? Okay, yeah, and again, like these filters can be combined to make a prediction of the image contents. So in the future, if a new image is passed, and most of the filters that apply to that image produce junk, but these three produce something consistently, then the computer can say, I think I'm looking at a horse. And so let's take a look. I'm going to skip forward to look at what that looks like in code. I'll start by saying, remember this algorithm. You're making a guess, you're measuring your accuracy, you're optimizing your guess, and you're repeating. So the algorithm is going to look just like this. We're running a little bit behind time, so I'm going to skip quickly through these. So here's the code. So this is the code for a very simple convolutional neural network. And it's a very fancy term. Convolutions is just another term for filters. And this is a neural network where we're going to create and randomly initialize a bunch of filters, and then we'll have the computer over time learn the best values for those filters that will match the incoming labels. So I'll start with this. So first of all, it's a sequential, as you can see at the top. And sequential just means this is a stack of layers, and your data is going to come in the top and pass through them and come out the bottom. And the first type of layer, and you can see three of them here, are called a conv2D. And that just means a two-dimensional convolution. And a convolution is just another word for a filter. And quickly, in summary, the way that a filter works is that if you think about every pixel in the image, that pixel has a number of neighbors around it. And what a filter does is you apply a multiplier to that pixel plus its neighbors to get a new value for the pixel. So there's very common filters that you see like on Instagram and those kind of things for sharpening an image or for changing the colors, and that's all that it's doing. But there are then fancy filters that you can do that maybe detect vertical lines or horizontal lines or diagonal lines using that kind of mathematical operation. But what we're doing here is we're just randomly initializing a bunch of filters, and we're going to learn over time. So here it's like we're going to randomly initialize 16 filters that we're going to pass onto the image. And one thing that I just want to say here, this max pooling, you're probably wondering what that is. Well, that's a way of compressing the image while you're enhancing the features. So max pooling 2.2 here, all that it's going to do is you're going to take every set of 2x2 pixels in your image. So if you imagine the top left-hand corner, those 2x2 pixels, and whichever value is the biggest, we'll keep that and we'll throw away the other three. So in this case, the max pooling 2D of 2.2, that's going to quarter the size of the image, but it's going to keep the maximum value pixels. Now, why are we doing that? Well, because we have multiple layers of convolutions. So the first thing that you can see here is that we have 16 filters. So you imagine you got a big image, and here we're saying the image is 300 by 300 pixels. So we have 300 by 300 pixel image. We've 16 filters that we apply to that. Is going to give us 16 new images. The next layer has 32 filters that we apply to that, which is, so we're going to have 32 times 16 images coming out of that. And then the next filter has 64 filters, so we're going to have 64 times 32 times 16 images. So we're going to have a lot of images by the time we reach that third layer in the network, which you can see, like the third layer in the network that you can see right here. So the idea behind max pooling is that, hey, look, we're going to be adding all of these images. Let's make them smaller as we go along. So if you can imagine, like we have a 300 by 300 coming in, the axes on that are going to be halved. It's going to be a little less than half for subtle reasons I won't go into now, but you know, it's going to be like roughly 150 by 150, then 75 by 75, then 37 by 37. So by the time you reach the last layer, you have, you know, many hundreds, maybe thousands of images from the original image. So you want them to be smaller, but the features to still be there. So that's why you got a thing called max pooling. It's just a little hack to make your life a lot easier. Then underneath that, you see dense, and when you've seen neural networks, you've generally seen dense, where you see all the neurons and they're all connected to each other. That's greatly used for classifying a content. And so out of this, we have the results of all of the images with all of the filters, then being fed into a dense network, which does the hard work of matching, saying, okay, I got all of this data, and I know this is a human. And I've got, you know, so let me match that to it. I've got all of this data and I know that it's a horse. Let me match that to it. And then in some ways, the most important ones that you want to look at is the very final dense layer. And the number of neurons here is usually the number of classes that you're trying to detect, with one exception. So for example, if you're trying to detect rock, paper, scissors, there's 3 classes, you'd see 3 neurons here. My example of a disease where it's like maybe 10 different diseases, you'd see 10 neurons here. The one exception is that you can do a little bit of a shortcut, that if you're only doing 2 classes, and in this case I am with like just horse and human, you can actually use an activation function called sigmoid on that, so that you can do it with only 1 neuron, where the idea is that that neuron will be pushed towards 0 for one class and pushed towards 1 for another. So that's why, even though I got 2 classes here, you only see 1 neuron. And then the next part of it is like, as you want to compile your model, but the important things to look at here are what called the loss function and the optimizer. So remember this algorithm: you make a guess, you measure your accuracy, and you optimize your guess. So the loss function is what measures your accuracy. In this case, we're saying my loss is binary cross entropy. Here's where a lot of the math of machine learning comes into it, and also in the optimizer. But the nice thing about when you're doing it in TensorFlow is that you don't need to know that math. There's a whole bunch of these loss functions have been created for you, and you can just pick one. Like in this case, I picked one called binary cross entropy. You might ask, well, why did I pick that one? The clue's in the name. There were only 2 classes. This is a binary loss function, which is great for measuring 2 different things. But as you learn more TensorFlow, you'll see there's more loss functions, and you can experiment to see which is best for your scenario. And then the other one, of course, is the optimizer. And in this case, I'm using an optimizer called RMS prop, which is root mean square propagation. And that's the thing that optimizes your guess. And then if you've heard of something called back propagation, what happens at this point is that I have all of my filters. They were initially randomly initialized. I got an accuracy out of them. My optimizer then, you know, was able to figure out, hey, I think if you set your values to this, you'll get better results. So the optimizer resets the values of all of these filters through something called backpropagation, you know, to be able to go back up through the network to set all of these, so that, you know, your next time around, your guess will hopefully be better. And then you'll see something called model.fit when you're looking at code. Here's my training code. And you'll generally see this thing called epochs equals 12, or epochs equals a number. And all that is the number of times that you repeat. So if we go back here to make a guess, measure accuracy, optimize your guess, and repeat. So when I've written this code, it's just going to do that 12 times. So let me show this as a simple demonstration. I'm going to switch to another screen for a moment, if you just bear with me. And I will share that one. I have one that I'm going to stop this. I'm going to share another one. I have one that I created earlier so that we can see. I'm not going to train the entire model now. If we could switch back to my shared screen, please. There we go. And let me zoom in on this. Oops. zooming on the wrong window. Okay, so I'm going to come over here and show. This was a model that I trained just a little bit earlier on, where I don't have time to go through the whole thing now. But this was horses or humans, so where there are actually two classes. So in this case, I designed the model using similar kind of code to what we just saw, where I have convolutions followed by max pooling. They all get fed into a dense layer, and then that dense layer gets fed into a final dense layer for the final classification. But what I want to show are the results. So as I was training, and if you want to explore how training works, these are the numbers that you want to look at. So I'm on the very first epoch here, epoch 1 of 15. It made a guess, and that guess was right 52% of the time. So again, we have that concept where it's making a guess, it's measuring the accuracy, and it's optimizing the guess. So the first time through with this network, there's only two classes. You'd expect it to be close to 50%. It was actually 52%. So then the optimizer kicked in based with that, with the values of the filters, the value of the accuracy, and the optimizer function itself, and said, okay, let me tweak the filters to see if we can get better. Back propagated it new values through to the filters. And then the second epoch went through, it made a second guess, and then we saw it was up to 57%. I hope that's large enough for you to see. Let me move over so you can see it a little better. So that went up to 57%. So now after two epochs, my 50% random is kind of, the odds are moving in my favor, where it's become 57%. I repeat that again for a third epoch, and it became 65%. And as I continually repeat, you'll see it will generally be growing, but not always. Sometimes the optimizer says, like at this point I was at almost 71%, and then it back propagated a bunch of new values, and the result of that actually ended up going down to 66%. So it's not always going to iterate closer and closer and closer to the result. And this is the kind of thing you want to keep an eye on. And by looking at your optimizer and tweaking the parameters of your optimizer, because there are parameters in it, but over time you can see it began to climb again, and then sometimes would dip, and then began to climb, and then sometimes would dip. But by the end, I only ran it for 15 epochs. I did a very simple model. As you can see, it was only 13 seconds per epoch, so this just took a few minutes. But it grew from 50% accuracy, which would be a coin flip for two classes, to almost 79% accuracy. So we begin to see that it is learning, and it is going through that paradigm, and it is iterating through those things to be able to learn and improve on the initial very rough guess. So, and if I want to kind of just give a quick demo of this, I have some code here where what I can do is I can upload an image from my computer. And I have one that I downloaded earlier. The clue's in the name. It was a horse. And let's see what the model thought. I'm uploading. Oops, there's an error. Oh, I beg your pardon. I can't demo it now because this collab had timed out. So the model has lost and hasn't been trained. But you can download this notebook and try it out for yourself, and then you'll be able to see. One of the things is that this is a very difficult problem to solve, horses or humans, in being able to understand the images that are within it. And this was one that I trained very quickly in just a couple of minutes. You'll see it gets it wrong a lot. And I deliberately created this data set to make it a very difficult one for you to train. And it's quite a small data set with only 1,000 images. So it's really fun if you want to dig into kind of learn about convolutional neural networks and computer vision, so that you can build networks that are actually able to do pretty well with it. And like I said, looking at the accuracy as it changes over time is very important. So you can see how your model is learning. Looking at the loss is also important, but it's hard to understand the units because different loss functions have different units. So you can't really say 0.7 somethings. The one thing that you would want to do with the loss function is just make sure that over time it is going down. So high loss is low accuracy in general. So you want to look at your loss and see it going down. You can see it's trending down, 0.7, reaches 0.55, reaches 0.49, but it does go up and down a little bit, which means I probably need to tweak my neural network in this case. But overall, keep a look at those two figures and you'll see that your network is training over time. So with that, we're almost at time, so I can take some questions.
Awesome. Thanks, Lawrence.
Thank you.
Awesome. Great presentation. And sorry the demo didn't work. it looked like it was pretty fun. We do have some great questions from the chat. And let's see. Let's pull out this one first from Rohan. What are some math prerequisites that you recommend getting into? First, because as we learned earlier, much of the audience at the moment are more intro level to machine learning. So
Right.
what are some recommendations, like how to get started with TensorFlow 2.0?
Yeah, so math prerequisites for my book, 0. There are no math prerequisites, first of all. So, and to get into TensorFlow 2.0, really, to get started with building these things, you really don't need any. When you want to kind of understand and tweak your loss function and tweak your optimizer, as I was showing there, it begins to be useful to understand how it works under the hood. The paradigm that I always like to use is that you can be a database programmer without knowing how a database works. But if you know how a database works, you can be a better database programmer. And machine learning can be no different in that regard, so that you really don't need to understand the math behind it to know how it works. But once you begin to get into understanding the math, and particularly how optimizers work, you can be a better ML engineer. You'll see, in my book, I do almost no math. For the convolutions, I explain a little bit, like I was talking about in this one, how you multiply out the pixels by their neighbors. And I have one example where just the closest that you'll get to math is in algebra, the formula for a line, y equals wx plus b. And, in the very hello world example of machine learning that I like to show is that you'll learn y equals wx plus b for a set of numbers, but that's about it. So yeah, I think to get started and to get coding with this, you really don't need any math prereqs.
Gotcha. Yeah, Josh shared with us yesterday, dipping into the Pythagorean theorem, and so just the entry level stuff like that is great starting steps as well.
Yep. Yeah, but they don't let a fear of math stop you from doing this. I mean, it's been 30 years since I did high school calculus, and actually more than 30 years. I'm giving away my age. And when I first started doing machine learning, and I saw it was like calculus this, calculus that, calculus the other, it actually turned me off. But then once I really started digging into it and taking a code first approach into it, because I'm a coder, not a mathematician, I was able to be pretty successful with building some stuff. So I recommend the same if you're not a mathematician, don't let this scare you off.
Awesome. We did have some questions from the audience during registration. And so this one came in. What are some recommendations for model monitoring and some best practices around that?
So for model monitoring, I'm assuming just at runtime to see how the model's behaving. I'd say similar to when you're training a model, you just really have to keep an eye on errors that the model has done and understand those errors and collect those errors and start. You probably want to build another model based solely on the errors so that you can understand the errors and things like that. So it's, like any piece of code, don't think of a model as being anything sufficiently different. It ends up being a binary blob with these the rules learned within it that I was talking about. But like any piece of code that you deploy, it's important for you to kind of monitor and keep an eye on its errors, first of all, so that you can gather data about those and fix them. But then also, for example, false positives that come as a result of biases, or like true negatives that come as a result of biases, that you also want to keep an eye on that, because your model might be working as intended, but it's doing something wrong. And, so you need a feedback loop for that kind of thing as well.
Gotcha. And we have a question from the audience here from Any Vibrant. How do we ensure our model accounts for diversity and inclusion? So like in your example, you were showing, we can recognize that these are legs. How would you handle that?
That's a great question. Not all humans have legs. You're exactly right. But even beyond that, not all pictures of humans have legs, right? You're looking at me now and you can see me from the shoulder up, and you still wanted to recognize me as a human. So one of the things that we do that is there, and I didn't really go into it in this talk, but there's a thing called image augmentation that you can work on. So for example, if in my training set, all of my humans had legs in the images, but I wanted to be able to recognize humans from the waist up, for example, as well as be able to recognize humans who might be in a wheelchair or who don't have legs or those kind of things. There's a thing called image augmentation, so that on the fly, while your model is learning, you can do things like zooming into the image, cropping the image, and all that kind of stuff. I didn't get to that today. There is some stuff that I cover in the extended version of this talk, or it's also in my Coursera courses and the book around this, where you can see how you can train, for example, like, my image was full people standing up, but sometimes you zoom, so it's just waist up, so that it will begin to recognize features based on that. I want to just use a very simplistic example for this 0 to hero where I was showing the legs, but and then of course, how do you ensure your models account for diversity and inclusion? You also want to have as diverse a data set as possible. So, zooming in just to show from the waist up isn't sufficient to show maybe somebody who's wheelchair bound or those kind of things. So you want to make sure that as you have training sets that you have the proper sets of data as well.
Definitely. A big +1 to that one. It stems from the data.
Yeah, so before we go on to the next one, it definitely stems from the data, and I agree with you, but we can also lead ourselves into a false sense of security by just thinking, diversity issues are just making sure your data is diverse. There's another common pitfall that people sometimes do, and when you do something called transfer learning, where the idea is that you're building a model based on features that were extracted from a previous model, but if the features that model was trained on, the features that it extracted had biases inherent in them, then even though your data might be quite diverse, you could still have problems in your actual model. So there's, you really need to look end to end, and it was part of what we were talking about in the keynote yesterday, like, for some of the fairness practices, go back and take a look at that there's a bunch of tools that will help you with that.
Awesome. And then final question here. So there are many more questions, but in order to hop over to the next speaker and be conscious of your time, Ben asked, in models you are building, tweaking manually, which loss functions, activation functions, initializers, constraints, optimizers are your favorites to try first?
Oh, well, I have to say it depends, because, it really depends on your scenario. If you're a vision model or natural language processing model, those kind of things, you're going to be using different ones. I generally don't have favorites. I find the Atom optimizer, though, is one that is very useful to start with. Because it has what's called it's like a dynamic learning rate. It can kind of tweak itself on the fly, so it can get a little bit better instead of this static way of learning. If you have no gradient descent and how something bounces down the way your error can bounce down a curve, Atom optimizer is really good for that. But it generally very much depends. Activation functions almost always use ReLU on every layer except the last one, because ReLU is really useful in the sense that it just throws away negative values so that they don't cancel out with positive values. But ultimately, I would say it really depends.
Awesome. Thank you again, Lawrence, for, let me remove that one too. So thank you again, Lawrence, for sticking around or coming back and joining us for day 2. And hopefully you can stick around a little bit and answer some more questions in the chat.
Yeah, I'll jump over to YouTube now.
Pleasure having you. Yes.
Thank you so much.
And thank you again.
All right. Thanks, everybody. Bye.
Cheers. Thank you so much. And make sure to leave Lawrence some feedback. Here's the link again. TF Everywhere-survey 2. Remember the 2 at the end. It's different from yesterday's survey. Please continue to fill out yesterday's survey if you haven't yet. We greatly appreciate all the feedback you have. But up next, our speaker is Lee Johnson. She's a Google developer expert in machine learning. She's also a staff machine learning engineer at Slack. And she's going to be talking today about MLOps at the edge. So please help me welcome Lee.
Hello, everybody. My name is Lee, and like Kyle just said, I'm a staff machine learning engineer at Slack. Today, I'm going to be talking to you about a passion project of mine. Around 3 years ago or so, I set out on a mission to give my Raspberry Pi collection the gift of sight. There was one problem. I'd done nothing with computer vision. I had no experience, and the highest mathematical course I'd ever taken, I think, was linear algebra, and I'd taken it in about 9th grade or so. So these were some pretty big barriers to entry. I have a background that makes generalist engineering look like an extreme sport. I've been a database reliability engineer. That's an SRE, a site reliability engineer, but laser focused on the database tier. I've done infrastructure engineering, video games development, and web development. You can read about my journey and some of the materials that I've published to try to make this easier for myself. Over on Medium, I do a lot of work for Raspberry Pi because hands-on projects have given me the sense of fulfillment and the dopamine hits that I need in order to learn stuff. Okay, so if you're just starting out learning deep learning data science, I've been in your shoes. So around 3 years ago, I made this diagram to grok a convolution operation. The mathematical figures didn't really make sense to me, but this did. And now over time, I've gained the fluency, comfort, confidence of a practitioner, and I've got to work directly with people who have done advanced research in the areas of computer vision, having done masters or even PhDs. And you can do this too. Tweet at me if you ever need a cheerleader or you want to share some of your work so that I can get excited about it too. Today, I'm going to be talking to you about a project called Print Nanny, which is where I detect 3D failures and defects using computer vision with a model deployed to Raspberry Pi. This is a deep technical dive covering a wide breadth of material, so I'm going to fly right through it. But if you want to come back later, there are resources linked in the slide deck, so you can go down these rabbit holes as well. And if you find yourself wanting to dig deeper and ask questions, feel free to tweet at me or shoot me an email as well. Those links will be available at the end. So don't be alarmed. This is one of the 13% of data science projects that never made it into production. But as someone who's done a fair amount of production engineering, I looked at the statistic and I wanted to know why. Why do 87% of data science projects never see the light of day? And is there something that I can do to help? In order to study this, I started reading studies that were conducted. This one was conducted by Rackspace in December 2020, January 2021, so pretty recently. And it surveyed around 1,800 business and tech leaders spanning multiple industries, spanning manufacturing, finance, retail, government, healthcare, and many regions as well, Americas, Europe, Asia, Middle East, and Latin America. And the goal of this study that I'm citing is to understand the current state of machine learning adoption in the world at large, its usage, benefits, impact, future plans, and then the challenges that companies are facing in deriving value from machine learning. And if you look at this statistic, if you flip a coin, it's equally likely that the machine learning at a company is in the pre-production or evaluation stage. And then only 17% of respondents reported that they were confidently scaling AI and ML in production, and they'd moved into a factory model of adoption. So I wanted to understand why this is. What was making this so hard? And I've encountered just about every single one of these challenges at one point or another as a machine learning engineer myself. The ones highlighted in orange are things that I'll be talking about today in some way or another. And I want to draw your attention specifically to the shortage of skilled AI ML talent, because these are things that you can do yourself. There's a lot of access to resources these days, and I myself am self-taught, and I think having a practitioner's confidence and having solutions working in production are always things that are just as valuable as research. So you don't need to feel like you need an advanced degree in order to do these things, is what I'm trying to tell y'all. Okay, today I'm going to cover an example of machine learning applied at the edge as part of an embedded system used to control a 3D printer. The reason why I'm focusing on this is because in the survey, you can see about 1 in 3 of production machine learning solutions were applied to either an embedded system or some kind of predictive maintenance or predictive failure, usually as part of a larger mechanical system. And this is an example of both. So here is a picture of my tensors flowing everywhere. The blue areas represent participants in Print Nanny's beta program. So the blue areas represent an internet-connected Raspberry Pi with a camera attached to it, running at the edge in someone's home or 3D print shop, monitoring their 3D printer for failures. Really quickly, let me bring you up to speed on 3D printers. This is a really deep rabbit hole if you ever want to go down it. You can join at the hobbyist tier for about $200 USD, and this goes all the way up to the industrial tier. These use different processes. So the hobbyist tier is using a process known as fused filament fabrication, where hot molten filament is deposited, building up a print layer by layer. Stereolithography uses a different process where powder or resin is used to create a print and then is cured with UV. There are different types of 3D printers. The The fused filament fabrication types tend to create low detail, and they use lower cost materials. And then when you go up market to the stereo lithography printers, you tend to deal with higher cost materials. They can create higher detail print. And obviously the equipment cost is a lot higher. So I'm not going to be focusing on that today. I can't justify an $11,000 side project, unfortunately. So these 3D printers, the fused filament deposit versions, are extremely unreliable because what they do is they deposit hot molten plastic layer by layer by layer, and they build up a print. And that print might take hours or days to build up over time. The hot molten plastic is heated to a temperature of up to 220 degrees Celsius. And if you're tuning in at home and trying to do the mental math, you can cook a pizza at that temperature. Just as a reference point, it's very hot. So you're talking about a situation where you might leave a print unattended for hours or days at a time, and it heats to a temperature that can cook a pizza and certainly catch fire. So that leads us to requirement number 1 for this project. Do not rely on the internet being available. What if I told you the internet cannot be trusted? Relying on an internet connection to monitor a hazardous appliance that heats to the temperature of a pizza oven would make me feel less safe, not more. That's the goal of this project. The goal here is to sleep peacefully while Print Nanny monitors my print job, pauses any defect or failure so I can sleep. Okay, so here are the system requirements. We need to do offline monitoring. We're going to use a Raspberry Pi as our controller. It's going to be running a TensorFlow Lite model. It'll be hooked up to a camera, and that in turn will be hooked up to another hardware controller that'll modulate our print. Over on the cloud side of things, we're going to have some analytics telemetry going on. We'll do our model training, evaluation, validating, and collect performance metrics in order to determine is the model actually working or not. Problem statement. So the types of defects that we're going to be seeing are these small, subtle imperfections, ranging from like these blistering or layer warpings to variations caused by temperature. The molten material behaves differently depending on which temperature it heats up to. And this can be sensitive to within a degree Celsius or even less. Sometimes the imperfections look like abstract art. This is a really cool Flickr account. So these people take their failed 3D prints and stage them with like studio lighting and high quality cameras, and it's just amazing. To full-on catastrophe, here's a 3D printer that caught fire. We do not want this. Okay, requirements for training a model. Let's talk about some options that we have. So the simplest thing that we could do is predict whether a print has failed or not failed. And the input frame is going to be sampled and fed into a binary classification model, which predicts whether the print has failed or not failed. It's a probability distribution that's output. And the output of this model answers the question pretty elegantly, right? Did the print fail? Did the print not fail? Over on the right, you can see clear examples of the frames that are more likely to fall in the failure category. Here's option number 2. This is a little bit more complicated. First, we're going to feed the image frame into a multi-class feature extractor. Then, like the model in the previous slide, the model attempts to classify the contents of the image. However, the classification task is not fail or not fail. The task is to classify between 6 exclusive labels. The first is print, which is fairly obvious. It's the 3D printed object. The second is raft. That's the circular throwaway material at the base of a print. The third is nozzle. That's the hot bit that extrudes molten filament onto the print object, building it up layer by layer. The next is adhesion. So that's a print object that's in a position other than the one it started in. Notice the exclusivity between those two things. Print object is in the position it's supposed to be in. An adhesion object is one in a position other than the one it's supposed to be in. Then there's spaghetti, which is a flyaway filament extruded from the nozzle. And that typically follows an adhesion event because the filament is built up layer by layer by layer. And if the previous layer does not exist, you'll end up with this funky flyaway stuff called spaghetti. So this approach is a lot more technically complex than the first, both in terms of component count and moving pieces. The problem is also framed as a time series problem. So what we do with the bounding box data is apply a smoothing filter to it, known as a Savgol filter. And then what we're doing is we're not attempting to predict fail or not fail, but instead looking at the cumulative health of the print and then trying to make trend statements using a polyfit model. So you can see whether the health score is increasing, decreasing, or staying about the same using that cumulative score. So I want to do a really quick exercise, and I hope my DJs can collect this information. I'll look back at it later. Which model would you implement? You have to prototype to production. You want to get something in front of an audience as fast as possible. What do you do? And keep in mind, I'm developing a brand new data product. In order to get over the production hump, I want to get a model into production as fast as possible so I can measure real-world performance and improve it for the problem I'm solving. So optimizing for rapid iteration, which model is going to be the most straightforward one to train, deploy to production, and improve based on its real-world performance? Post your answer or explanation in chat. If you want to discuss this long form, tweet at me. I love talking about this stuff. Okay, let's talk through the implications really quickly. Earlier, I said that the binary approach was simple. It's deceptively simple. Here are the challenges using a binary classifier for this particular problem. Machine learning algorithms need really good data to be performant, garbage in, garbage out, and that's all machine learning algorithms. In particular, the more complex the problem you ask, or the more complex the question you ask, the more data skew is going to impact your answer. So if we're asking the machine learning algorithm to answer the question of, is this print failing right now? There are so many determinants for that outcome. And a skew in training data can encode bias for answers that I don't intend. For example, my data set might contain failures where the filament is blue in all failures. And so the model learns that blue filament constitutes a failure and thus generalizes in the real world. Well, if you're printing with blue filament, you must be in a failure state. Obviously, that's the encoded information in the model. So even if I do get this solution to the point where it generalizes well, it's well optimized, trained on a well-balanced data set with augmentation, synthetic data, the question posed is still not great. The question is based on this one input frame and asks, is the print failing? Or at what confidence threshold do we consider the print a failure? And like any metric, this measurement can flap. So drawing a conclusion from this single flapping data point will create nuisances for my customers, especially when the algorithm is in an unrefined state. Okay, so let's talk a little bit more about this ensemble. Instead of one complicated question, is the print failing, machine? We're asking a series of simple questions, and we can reason through each of these algorithmically. By breaking out each question posed to the model, the results can be measured and improved with more granularity. It's easier to improve answers to what things are in this image than is this print failing? I can analyze the detection confidence of things like raft, spaghetti adhesion to know if my model is overfitting for a specific filament color, printer type, or any other dimension that I'm collecting data about. Measuring time series data also makes the ensemble more reliable than a single point in time prediction. I'm not boxing myself out of binary classification either. In an ensemble, if I wanted to, I could train a binary classifier using these interpretable features and gain a deeper understanding into the bias encoded into that classifier. Okay, let's understand my audience very quickly. They are primarily small-scale manufacturers. They're often operating out of garages, basements, really cheap warehouse space. They sell bespoke designs, usually with a fixed range of modifications, like letters on a dog bowl, shapes of a US state. There's a product skew associated with some of the data, so that's a dimension that you can break out on the data. Among hobbyists who end up using this data product, I'm most interested in the ones who have kind of an entrepreneurial disposition or might try to do their own startup with regard on Etsy or Shopify or eBay. So that's one way where I can go up market and level my customer base is by segmenting them and trying to focus on people who could become small scale manufacturers. And here's the opportunity to innovate in this space. When the pandemic shut down global supply lines, large scale manufacturers started turning to local scale print shops to reproduce parts and keep assembly lines running. For example, I spoke to a gentleman who's exclusively 3D printing automotive parts like dashboard components, instrument casing, and passenger side mirror enclosures. On the right, there's about $20,000 of 3D printing hardware in the photo. And he exclusively prints modifications and upgrades to Nerf guns. So we're going to use machine learning to apply lean manufacturing principles inside of the small-scale manufacturing industry and reduce waste. Okay, let's start. We're going to prototype the path to production. We know exactly what we're building and who we're building it for. And then for each stage of the data product's maturity, I'm going to be evaluating what I can delegate to cloud operations and then what I need to focus on and build myself. When I think about cloud solutions, I try to give them what I call undifferentiated heavy lifting. So that's the stuff that's really hard that I don't want to do myself. It has no value add to my product, undifferentiated heavy lifting. I think I stole that from Dave Hahn at Netflix in his How to Do DevOps talk, which is a great talk if you're trying to think about how to make engineers more productive without setting up barriers in front of them, in front of production. Okay, prototyping the path. Prototyping the path, by the way, is a sentiment at Slack where we try to build solutions and measure them incrementally rather than building the most perfect thing and then releasing it out into the world. So this is going to sound obvious, and I apologize for this. When productionizing your first machine learning model, there are a few goals that I needed to advance the project towards production. I needed to train my model, export it to TF Lite. I needed to write a prediction loop that continuously sampled frames from the camera buffer and then output the bounding box predictions. And then from that time series of box predictions, I needed to smooth the data over some window, maintain an accumulator for the sum of print health, and then I needed some sort of control mechanism in order to shut off the printer. Finally, I needed a feedback mechanism so that people could tell me this print was stopped and it was a good decision, or no, this print shouldn't have been stopped. It was a bad decision. The base components that I'm using are Raspberry Pi. I'm using a Raspberry Pi 4, in particular Pi camera. The 3D printer that I set out to get started with is a Prusa i3. And then there's a not pictured piece of hardware called an ENC Rambo. It's a motherboard for a printer. And the Raspberry Pi talks to the ENC Rambo over a serial port. Some software, a lot of it. Octoprint is an existing piece of software. And it's basically a web app, a web UI that controls a 3D printer and allows you to interact with it through a web interface. I built a plugin for Octoprint called Octoprint Nanny. And you can see it on the right there where pretty simple. You can just click start monitoring, stop monitoring, and it'll pause your print when a failure is detected. I also built a web app to keep track of beta invite requests and other stuff that might not necessarily make sense to track in Octoprint itself. Data is hard. I went out to YouTube for my data, and you can do this too. I use something called YouTube DL, and I don't have enough time to get into the controversy around this specific tool, but always check your licenses if you're scraping data from the internet and make sure that the licenses match your usage, especially if you're a commercial user. To hand label things, I use Microsoft's visual object tracking tool, about 3,000 frames, 5 labels, and I averaged about 3 objects per frame. The important thing about this slide to note is that I discarded half of my data. So about half of the data that I collected, I just threw in the garbage. It wasn't good enough. This tool has convenient exports, in particular to TF record and CSV are the valuable ones. So the one that was easiest to work with was CSV. The light preprocessing only some light preprocessing was required to get the export into a format expected by GCP AutoML. I chose AutoML as my initial training platform, even though I could train an object detection model myself and knew that, all right, I'll probably want to use like a mobile SSD architecture or a mobile net feature extractor with an SSD localizer as my architecture. I hadn't yet validated the problem, so I used AutoML in order to do that. AutoML is an automated machine learning product offered by Google that lets you upload a data set, as you can see here. And I've uploaded my labeled data set. And after a little bit of pre-processing, which you can inspect later, I'm able to import the data set from Google Cloud Storage into Vision. And then from there, I can kick off model training and define a few optimization parameters. So what I did is I optimized my model for just a middle of the road trade-off. I spent about $127 training this initial model. So in terms of prototyping the path to production, this was very inexpensive compared to even taking an hour or two of my own time to try to train a machine learning model. And the pros here to using the AutoML Vision Edge product were that it could export to the formats that I wanted to prototype with, TensorFlow Lite being the most ideal one. Really quickly, just to go into evaluating the baseline of this model, I wanted to understand how it would perform in the initial production run. From this view, I can see F1 scores in the left-hand column, and I can see confidence in IOU thresholds. I can see the performance at these specific confidence and IOU thresholds, and I can slide these around in order to understand the model's performance across the precision recall curve. I don't have time to get too deep into these metrics right now, but please tweet at me if you're curious. So over here on the left are F1 scores. That's a type of weighted average of the positive class measured at the intersection over union threshold, in this case, 0.5. Of all my classes, you were going to note that the nozzle has the lowest ratio of detected area. And this is going to have an impact on the F1 score and just about all of the metrics compared to other labels. And the reason why I'm noting that, I'll come back to later. So here's the precision and recall measurements. Just quickly, what precision and recall mean in relation to my problem. Precision is an expression of true positive predictions in relation to false positives. And so for me, having a high precision metric here means that I'm going to have a low false positive detection result using this model at this specific threshold. Recall is an expression of true positives to false negatives. So this recall score of 71% means that in the evaluation set, 29% of the objects I labeled were not successfully detected. In other words, the model didn't generalize very well. That's okay, though. If you want to do an additional analysis, this is a cool trick that you can do. You can actually load the evaluation metrics into a Pandas notebook in a data frame. I have some sample code that's linked in the slide resources if you want to go and do this yourself. This can give you more info than you can get in just the UI. If you want to go and explore the actual graph exported by this model, you can view the saved model with TensorBoard. You'll have to export it first. So what you do is you can export the saved model from AutoML, extract the graph from it, load the graph into TensorBoard, and then you can go spelunking. So in this case, I wanted to go dig into the feature extractor and see exactly, well, what made this faster? Why was this so fast? Or why was it the recommended model by Cloud AutoML? And I found, the feature extractor is called MNASNet. It refers to a neural network architecture that benchmarked better than MobileNet, which is the kind of state-of-the-art model that has good performance benchmarks at the trade-off of accuracy and latency. So this network implements what's called a separable convolution operation. I don't have time to get too much into this, but it's good to understand what the operations are ideal and not ideal for. So this one, for example, is not ideal for grayscale input. And yeah, you can explore these links yourself if you'd like. Something I noticed at this point was that I had really poor quality data and I needed to prioritize improving my dataset. For example, I had mislabeled a lot of nozzles, and I could see this in the AutoML data exploration. So after I saw this, both that my bounding boxes were too loose and that I'd failed to label nozzles at all, I went back to improve the data quality, and I added the TensorFlow.js model to the visual object tracking, or the visual Microsoft's VOTT tool, in order to automate this process for myself and make it a little easier. I wrote an article about how to do exactly this. What you're basically doing is taking the TensorFlow.js export of an AutoML model and using it as a guidance model to produce bounding boxes in a process that would otherwise be completely manual, and actually host this online so that my virtual assistants can go and label these boxes for me. Okay, really quickly, let's break out the confidence scores and give you an example of the approach that we took here. So I have confidence metrics detected over time. And the feedback that I give my users is, did Print Nanny make a good call? Did it not make a good call? I've got to fly through some of these slides because I'm taking a little bit too much time. So I apologize, but if you do have questions about this, please tweet at me. Okay, we're looking for the sum, the cumulative sum of health versus not health. So we're going to look at print and raft versus things like spaghetti and adhesion. And you can see right here, oh, well, this is where things did not go so well in this print. Next, use something like a polyfit or just another curve fitting approach in order to determine in a cumulative health, like an aggregate accumulation of the health of the print, when did that accumulator start to go down? And so the exponents on something like a polyfit curve give you information about that, and you can see exactly where the failure is detected. Okay. And then here's our prototype. We're going to need to monitor print jobs, pause failures, and accept beta signups. So there's a very simple architecture here. I've decided to use Kubernetes to host my Django app because I know that this architecture is going to get very complex very fast. We did it. We're in production. We're part of the 13%. Yay. Now we need to make it better. Refine the results, add more value. The first thing that I did was exclude irrelevant detections. This is technically this result is not wrong, but it's certainly not right. I immediately noticed 3D printed objects outside the print bed were being included in health score calculations. We don't need that. I added the option to calibrate Print Nanny by dragging a box around the area of interest. The calculation used to exclude irrelevant detections is the same one that's used to calculate loss for this model. So it's a good exercise to go through. Then I needed continuous learning. No big deal. I need to publish telemetry data, process the data stream, retrain the model, run experiments, deploy the model, and then monitor it on top of what I'd already built. The technology that I used was Google Cloud IoT Core. So this is where undifferentiated heavy lifting comes up again. This is edge device management and data ingest. So it supports a protocol called MQTT, which is a message-based protocol designed specifically for IoT devices, which are flaky and might be deployed at the edge of your network. It has some certain security properties that were very valuable to me. Especially that I could provision each device with its own key. From a security perspective, certificate management is a very difficult thing to do. So the fact that Google Cloud IoT Core gave me a way to do this meant it would be easier for me, less stress in my life. The platform also offers a way to manage devices remotely. And finally, the unifying thing that I needed was the gap between MQTT, which is just a message broker, and every other data ingest point was bridged by Google Cloud IoT Core. They automatically sync messages in the MQTT broker to pub subtopics, where I can then go and connect every other Google product and very easily subscribe to messages published by my devices around the world. Okay, so the initial setup for this looks something like this. I'm going to gloss through this because it's just a traditional key exchange. And once the device has been provisioned with a unique key, it can then open up a long-lived MQTT connection. And the important thing to note is that MQTT is a duplex stream. So when the device opens the connection, it can send data, but it can also receive data. And this is a way of receiving data at the edge without necessarily having to open ports or other insecure things. So my users in their homes with their internet connected cameras are very safe. The MQTT topics are like any other pub subsystem. So you can create topics and then interested parties can either subscribe or publish on those topics. In this case, I've got topics for config, frame buffer, and bounding box telemetry. I can sync those to other analytic products or to Google Cloud Storage if I want to store them in the long term. Apache Beam is what I'm using to do a lot of the stream-based processing. It's got a unified batch and streaming programming model. So if you sync your data to GCS and want to process it in batches later, you can use the same code that you use in order to process it online. And the simplest pipeline that I built, the very first one, was to take a pub subtopic, my frame buffer and bounding box telemetry, just group it by device over a fixed interval window, 10 minutes or so, pack TF records, and write it to GCS. And that would be my training data set later. If you're solving a computer vision problem, you want to be able to reliably reproduce your results down the road, I recommend using TensorFlow's object detection API. I started with an AutoML model, but I knew that I was going to be leading up to this. This is a component of the TensorFlow models repo. It's got a lot of interchangeable backbones, meta model, hyperparameter tuning, a zoo, and most things work with the TF distribute strategies for GPU and TPU out of the box. Going to keep flying through this stuff. I needed the model version framework. Thankfully, I'd already started using Django. And about 100 lines of Django code, I was able to set up something that would let me label artifacts, configs, dataset, and then boom, just push those to the cloud from my GPU workstation, which I treat as a server. Here's the infrastructure as code pieces. So I just said I treat my GPU workstation as a server. It's configured with Ansible. And then I use Terraform in the cloud. Tweet at me if you are new to these technologies. If you're a data scientist and looking to get started with something like Terraform, it can add a lot of sanity to your life. So here's my MLOps Lite. It's some scripts, a cron, and Django. Not super complicated yet. I've got my really beefy GPU workstation machine, which is, even though it's sitting on a desk at home, I treat it like a server. And I've got this semi-automated pipeline where I download some TF records that I've sunk from my Apache Beam pipeline. I train, takes about 24 hours, and then I can upload the finished model when it's done. I manage experiments through a Django admin panel. I measure latency with something called Honeycomb. It's an application tracing utility. And there are other options for application tracing as well. This one's one of my personal favorites. And if you want to read a little bit more about tracing at Slack, Suman has written an amazing article about how we do tracing at Slack scale in order to try to figure out where exactly problems in our applications occur. The most valuable utility here is being able to select portions of your traces and then drill deep into heat maps by latency. So I can select devices with high latency and then group by. So I can see if they're running a particular platform, a particular version of my code, or if they're on a particular device model, maybe a Raspberry Pi 3 instead of a Raspberry Pi 4. And I can get that deep intelligence without necessarily having to do a lot of data munching and processing. Okay, here's the final refined concept where we've got continuous model training, deployment, and monitoring. Looks a little bit different than our initial prototype, but because we prototyped our way to production, our path was very clear here. And now the next thing we need to do is scale to meet customer demand. So right now, my customer demand exceeds capacity. I've got about 1,800 requests for this and only 200 invites sent. I'm drilling into to try to figure out who are the business owners, how many printers do we need to support, and other types of metrics that are all going to determine exactly how good does this model need to be and what type of distributed training do I need to build. Because I do need to build distributed training. I'm already putting in the work of tagging, versioning, and uploading metadata about my models to the experiment framework I've implemented with Django. The workload running on my GPU workstation is very close to the one I'll run on the cloud. And here are the key differences. Instead of a cron on my GPU workstation, I'm going to run cron jobs with a scheduler explicitly designed for running machine learning workloads with Kubernetes. That's Kubeflow pipelines. I've been training on one GPU, and many of the backbones included in the object detection API have been written with ops that can be accelerated across many GPUs and TPUs. Okay, so it's going to look a little bit like this. Instead of running all of this code on my workstation, we're going to build and deploy using GitHub Actions, build a Docker image, push the image over to the cloud. And now we've got some scale out mechanism I've put the work of running my GPU. I've put in the work of making my GPU process very repeatable. So when I'm ready to go and distribute this to the cloud, I'll just have to set up those pieces of infrastructure, and then I'll be able to use the same workload. A little bit more about TensorFlow Extended. This is the statistics. The thing that I want most out of TensorFlow Extended is statistics and data validation for things like anomalies and missing values. This is the piece of my production pipeline that's missing right now. It's extremely valuable. We're going to take the TF records that I mentioned earlier and run them through a series of generator process. Example gen creates from the TF records TF examples. Statistics gen gives you some really useful information about the entirety of your data set with just one line of code. You can look at distribution of values and play with these in a notebook. And the reason why I want to do that is so that I can use TensorFlow's data validation library in order to sanity checks of my data. Again, so TensorFlow Extended is also going to be the way that I do training and evaluation. And it takes this part of the pipeline takes two inputs that you see in the previous slide. You take the examples that you've generated and the schemas you've generated, and you can run those through transform. So some of the code that I've written to pre-process and transform my data, I'll be running in TFX. The trainer code that I run on my GPU workstation is going to be ported to a TFX trainer. And then finally, there's an evaluator. That's it. Very simple and straightforward, huh? The reason why I went through next steps is so that you can start to understand what I'm building towards and where this value is. I think I'm a little over.
Hey, thank you so much. It was great talk, Lee. We learned a lot about your project. There's a lot of fun comments back and forth around when you challenge the audience, which one would they pick, one or two? Most of them were saying one. We did have one person who was so like Ben here, where he was thinking through that, if you do cohort studies, where's it breaking down, stuff like that. Is that where you were thinking as well?
Yeah, that's right. Machines aren't that smart yet. Asking them a complicated question like, is this failing? It embeds the information of what constitutes failure into the model's weights, and that becomes very difficult to explain and introspect. When you start breaking out the answers to those questions or posing them in simpler terms, you can do cohort studies. You can understand that the raft label is appearing, has 20% less accuracy on a specific model of printer, for example.
Gotcha. And thank you for walking through like how you put together your project and stuff like that. There's like this question here from Rob. Are there any adjustments necessary for using an IR camera for the nanny as opposed to a visible light camera? How does that behave?
Yeah, totally. I didn't have enough time to get into some of the model architecture changes that are required, but you're going to need slightly different input processing for things like IR input and grayscale as well. One of the things that I tried to do early on, there's a lot of color variation in 3D printed filament. I've got about 10 colors myself. Can we just eliminate that? Can we just do grayscale modeling? So I'm still trying to answer some of those questions, and putting things like a TFX pipeline in place are going to give me the ability to reason about those because it'll give me that factory style of model production where I can just very quickly ask and answer those questions, experiment in production, and see real world results rather than trying to reason about it in a theoretical way.
We have another question here from Kevin. How many hours would you estimate you spent coding and preparing to get to this beta stage, not including your training time?
Oof, the presentation for this, I estimate about 1 hour per minute of presentation preparation, and that's just for the presentation. That's not anything that I actually built. That was just how to talk about what I built. Everything else was probably about somewhere between 150 and 200 hours. which is a lot for a side project. This is a nights and weekends source of passion for me, but it's driven me to do and learn new things that I can bring back to work. For example, we're still evaluating whether TFX is going to be something that we want to use at Slack. And for Slack, that's a higher dollar bet than the one that I'm making in my personal life right now. So if I'm able to reason about how to use TFX for a very small scale project like this and be successful with that, I can take it back to work and save us some of the troubles and hassles.
Awesome. That's a great point of view too. We're working on some of these side projects as small little bets to see like how you can improve your work and from different angles. So that's a great takeaway. We did have, I don't have it at hand, but there were some questions earlier about so what's it like being a GDE, and like how what was your experience becoming a GDE? Do you stuff like that?
Wow, I think it's been truly amazing. The thing that sticks out to me most is I remember going to GDE Summit in the before times and then looking up at a map where every single GDE was a pin on the map and realizing just how worldwide the group was, how many languages were spoken, how just many different cultures were represented. And I don't typically have access to that because I work at a company that's located in a couple of regions. For better or worse, we spend a lot of our time at work. And then I live in the United States. So my access to many cultures is fairly limited. And that's so important when you're a machine learning engineer and trying to reason about how to algorithmically solve problems. You want to make sure that you can talk to and see as many perspectives as possible. And the GDE program has given me that.
That's awesome. Another question about your project here from Rob. Have you considered adding a second or third camera, maybe with a different view? Is this a good idea or diminishing returns based on your findings?
That is a really good idea, and it's one that I've explored. So that type of two-camera computer vision, the branch or discipline is called stereoscopic computer vision. And it's typically used for depth perception. You'll see it in a lot of autonomous car computer vision companies, say it 3 times fast, are trying to use 2 cameras in order to infer depth. And the way that you can do that is by taking a left camera and a right camera, and there's going to be disparity between their observation points. And you can use that to infer a depth or point map from the difference between the two. And it can give you more details about the texture, or it gives you an extra dimension of data to work with, right? So yes, I'm absolutely looking into stereoscopic. And the board that I'm using in particular, the Raspberry Pi 4 compute board, has 2 CSI ports, CSI being the thing you plug a camera into. So you can plug 2 cameras into it instead of 1. I'm excited.
It's very cool. Yeah, I haven't messed with the Pi 4 yet, but that's exciting to hear. We do have another question here from Ryan. What an awesome project. Are you planning to add the ability to send a notification, email or otherwise, to the owner to confirm a failure, so that way you can authorize stopping instead of just auto stopping? It would authorize the stopping of the print.
Yeah, that's a good idea. The authorization point isn't something that I have right now, but that is a good feature to add. Right now, you can get an email or a UI notification when a print failure. So it'll tell you when an action has been taken. My first employee also just added Discord notifications, which is sitting in a pull request right now. I got to go review after this. So very excited for that.
So it's already on the way, and I assume it's open source, your project?
Yep, 100% of the code you see here is released under AGPL. So it's totally open source. You can't use it for closed commercial purposes, but you're more than welcome to grab it, remix it. The source code is linked in the slides for this. There are a couple of different components ranging from Terraform pipelines, data flow pipelines. There's the web app, which is Django, and then the Octoprint plugin itself.
Gotcha. Since you dove into this, and it sounds like, with 165 hours, it was kind of a big step for a side hobby project. Kevin asked, what size of a project would you recommend somebody who's just beginning with machine learning Like, what? Yeah, how would you recommend like the scale of that project to be?
That's a really good question. Yeah, I wouldn't recommend starting 150 hours. This was a test for myself to see if I could take some of my hobbyist computer vision projects one step further. I have, if you're interested in computer vision and Raspberry Pis, two obsessions of mine, there's a tutorial I've written about pan tilt mechanisms on a Raspberry Pi. So you can use a pan tilt set of servo motors in order to track a moving object. And I've designed that tutorial so that you can do about an hour quick start. So it's one that you can do on like a Saturday, or if you have a class that you're teaching maybe with young kids and you're trying to give them a hands-on project, that might be ideal.
Awesome. Oh, thank you for that. And thank you for joining us today on TensorFlow Everywhere North America and taking time out of your Saturday. It was a pleasure having you. I learned a lot about your project. I know we've shared a little bit in the past about your project, and so it was very cool to get that deep dive, and hopefully have you on again for a future TensorFlow and machine learning event.
Thanks for having me, and thanks for letting me, excitedly ramble to you about my project. If you have any questions about how you can take the stuff you've learned today and use it in your own work, in your real job, let me know. I'm happy to answer questions. Again, I have an operations and a systems administration background. So if you're a data scientist and looking to adopt some of those skills, I want to help you.
Awesome. And hopefully you can stick around for a little bit in the chat. There's some more questions, comments flowing in still. But it was, again, pleasure having you. Please leave feedback for Lee on our survey, and we'll catch you again next time. Cheers.
Thank you.
Awesome. Yes. So remember, the survey link is here with the 2 on the end. Yesterday's did not have the 2. So you still have an opportunity to fill out the feedback for yesterday's speakers. But please provide feedback to all of our speakers here today as well. It helps them and us to curate better events for you like this one here. Up next, we have another Google developer expert in machine learning. He also happens to be a GDE in web technologies as well. We have Gant Laborde, who's owner of Infinite Red. He's a mentor, adjunct professor. He's been published, as we've heard from earlier speakers. He has a new book coming out soon on TensorFlow. So today he'll be talking about AI magic, AI from magic to science. So please help me welcome Gant.
All right. Thank you so much. And what a cool animation. What a great opportunity. TensorFlow Everywhere. Thank you, Google, for not only putting on this awesome event, but also lining up so many amazing speakers. A lot of the people who have spoken today have significantly influenced my interest in machine learning. And so I hope to actually return that favor to the next group of the community so that they can enjoy that as well. So TensorFlow Everywhere North America. First off, yes, indeed. I am a Google developer expert in web and machine learning. I am also the CIO at Infinite Red. And here I am being categorized just like Jason was earlier. I am a person. The JavaScript says so. So that is for sure. One of the things that I'm going to do a little bit different here is that I've seen such an amazing whirlwind of cool and interesting examples and technologies. And a bit of this can feel like a little bit overwhelming to some people or extremely exciting at the same time. So what we're going to do today is I'm going to take an approach where I'm going to say, I'm going to take this from magic to science. And the idea here is that for some of you, this is all just a magical, amazing, interesting world. And there's a lot of concepts that are there that feel that they are unapproachable, or they're just too intangible for you to actually get a piece of this. And we saw that we are breaking down those barriers. A lot of the speakers here, Lawrence, I have his book. It's a wonderful, wonderful book, and he is absolutely right. You don't have to have a PhD. You don't have to be a mad scientist with math in order to get started with these really cool ideas. And one of the cool things that we have here is that we've all experienced this sort of like, what is going on magic. And eventually we get into there and we actually understand it. I used to work at a place that had a program that we had to run every Tuesday. If you didn't run that program, the database would break. No one knew what that program did, and magic. And so that's the definition I'm going to be bringing here. It's the classic Arthur C. Clarke's third law. Any sufficiently advanced technology is indistinguishable from magic. And our goal today is going to be to break that magic down, to actually journey into a concept from a new angle. And I promise you, if you've been in machine learning for a while, you hopefully will still learn a lot of cool things from this talk today. But if it's brand new to you, I feel like this is a fun adventure as well. So we will see all the different pieces in sort of creating what will be a TensorFlow.js demo, and then we will hopefully do a live demo and actually see it function at the end of this. So I want to start this off with saying that the journey from AI, originally, we've had this concept of AI. It's existed in all of our worlds for a long time, and it was sitting there, and we needed this concept of like beating us in tic-tac-toe or all kinds of other aspects. Well, the problem is computers were brand new, and they took entire rooms, and they were doing amazing calculations that were far more important. And the idea of actually having digital data for a long time was absolutely, completely impractical. Just take a look back, let's say 20 years. If you wanted to have 100 pictures of a kangaroo, well, I guess you would have to find a friend or a pen pal, ask them to take hundreds of photos for you, and then email them over to you so that way you could have them. Today, if you want 100 pictures of a kangaroo, well, you just go to Google and then you do a search. So the data that we have now is much different. And so that's where this journey sort of begins. In the late 80s, we had some change here. Digital information became accessible, processing power started to come into the PC, and then algorithms started to adapt. And then in the 1998, there was a debut of what you will see in just about every demo of every talk that you end up going to about machine learning and AI, and that is the classic MNIST. So you had this amazing National Institute of Science Standards and Technology, which created this large data set of numbers and handwritten digits. And then you have the modified version of that, where it blew people away. How would you code something like this, where you could actually draw a number and then have the machine tell you what that number is? To code this from scratch, as any kind of developer who's never worked in machine learning, never worked with the data like that, this is a very difficult task to even start to break down. And now we use it all the time. This 28 by 28 image data set is constantly used. So that way we can actually see these numbers. This example actually coded and did on a mobile phone in pure JavaScript. It's not even using any convolutions in this example. So this example was super, super exciting and gave all kinds of energy and research towards what can computer vision, machine learning, multi-layer perceptrons, what can we build with all this? And what happened was people delivered. From MNIST, now we have so many different things that visual technology can do. You have image recognition, you saw object detection earlier, semantic segmentation, instance segmentation. We have so many visual variety that the idea of just drawing numbers is not as interesting as it once was. And then compound this with the fact that technology has just exploded into all kinds of different domains. We saw the opening of today was talking about sound. Everybody knows about GPT-3 and generating text, and of course, images are still around. So now we have this gigantic domain where we're trying to figure out what kind of cool things can we do with this. And the truth of the matter is, as you've heard from all the speakers today, is that our imaginations are the current limit of what we can actually deliver. But there's another aspect that we have coming in here that I've seen in the questions for today, which is the responsibility. So we have to worry about ethics, privacy, diversity, speed and accessibility. And then additionally, as you've seen with TF Lite existing on these edge devices and TensorFlow.js, we need to get these out in the field. It can't be a giant cloud of computers that can handle all this stuff, and you have to send it to the server and get that feedback back. So how do we accomplish all of these? Well, I say that one of the most interesting and most practical you've seen several times today is TensorFlow.js. And I'll make a quick case for that. For one, yes, it works on all kinds of different platforms. It's portable. It's offline ready, and people are interested in that. So no round trip. And I have to say, if you've ever seen some pretty fun websites that exist out there, there's some pretty silly stuff that you can do, and you can kind of get the concepts across in a much more fun, interesting, and exciting way. Of course, it's flexible. It'll work with text just as well as visuals and sound, but it's not a toy. It works with the GPU and the WebAssembly. And the last one, which I think is extremely important, is that when you're asking people to turn on their camera, there's this essence of privacy and ethics and where those images are going off to. And we already saw this. Quite a few images from some of the existing apps are being sent with people's actual notification off to servers and being collected and kept. Well, with TensorFlow.js, we can exist. And as you've seen some of the examples that you've seen so far, these exist directly on the client browser if you design them that way. And so that way we can actually keep all the information private. I am in love with this concept. And this is why I'm thinking, now we need a new demo for TensorFlow.js. And I think to myself, are we doing MNIST again? Are we just going to ask people to draw numbers and then tell them what number that is? I hate to say it, but that example's 20 years dated. So I challenged myself, and I think that this challenge comes in and tells you the story as well. Let's go ahead and create a data set, and let's go ahead and make it more fun and more engaging. So today, we are going to go through the process of these 4 steps for making a wonderful TensorFlow.js demo. First, we need something interesting and relatable. For instance, writing numbers was fantastic when everybody had to fill out forms, but we're a little bit beyond that. I can pull out my phone and do some amazing things with it. And object character recognition's just sort of expected. So we have to come up with something relatable and interesting. Secondly, we're going to need a lot of data to do this. It's going to be very important that we actually have a large data set so that we can train something. Then third, which I think is the most fun part, we go ahead and we train this in TensorFlow.js and we put it on a website so that everybody can access it instantaneously. Then the last piece of this, which I think is really important, is you have to show that that's not just a dead demo. That's not just a simple demo that doesn't actually do anything else beyond what you have there. It has to have this proof by mathematical induction to affect the next level of things. And so we're going to take this and we're going to escalate it just to show how much we can do with it after we've come up with the concept. So those are the 4 pieces that we're going to do today. And what I really like here is that we're going to start off with something I love. Personally, I am a Harry Potter nerd. So I thought to myself, why not do something with the Harry Potter universe? It's recognizable, it's playful in nature, it's not militarized like a lot of examples end up being. And one of the great kind of get out of this is that even if you don't know about the Harry Potter movies, you've never read the books, there's recognizable icons in this kind of sort of plan. And I think that makes it a lot of fun. So what can we do? I saw from the chat earlier, people were really talking about how much they love animals. So we could do this with the animals. We can have the Gryffindor lion, Hufflepuff badger, Slytherin serpent, and Ravenclaw raven. And wouldn't it be a cool idea if I asked you to draw an animal and then I was an AI sorting hat? The AI sorting hat on this website then identifies what animal you just drew and then sorts you into the proper house. So that's the idea. That's way more fun than drawing numbers, right? So I'd say that our first aspect here of interesting and relatable problem, that works out quite well. So now we have an idea, but we need to go ahead and we need data. Because as you've learned from today, we don't actually write the algorithms, we write the algorithms that train on the data. And so the data is actually creating the finalized result. So where can we get the perfect data set so that we can actually do this kind of fun thing? And the cool thing that happens here is that I love when large companies do this. Thank you, Google. Google has released the Quick Draw data set. It's under Creative Commons 4 license. It has human-made doodles for 345 different categories, and it is readily available. So I think that this is great, and they're already sized down to a 28 by 28. So now we have all these different drawings that have been made by people, and they look really cool. Isn't that kind of like hieroglyphics right there? And so this, take Gryffindor, and anytime somebody draws a lion or a tiger, they go in Gryffindor. A snake or a snail, because they kind of look the same, right? They will go to Slytherin. Ravenclaw gets a bird, owl, or parrot. And Hufflepuff gets the raccoon or the squirrel. Sorry, Hufflepuff. I know you're always left out in the cold. They did not have a badger, but the raccoon and squirrel are perfect enough. And we had 10,000 images of each. Now, one of the cool things I love about the way this, if you ever saw the old original NIST CDs that came out that did the original MNIST dataset, the background on the CDs was all the numbers in this really cool format. It looked just like this. Is now we're doing it with really cool drawings that have been created by the community in that data set. So that's tons of information. Now we have to see whether or not this works. Well, you could just start getting straight to it, but there's a couple of tricks we can use. We could use the TSNE, which is the T-distributed stochastic neighbor embedding. Whew. I don't say that very often. But what happens is this helps us identify whether or not our features are identifying or not. And one of the cool things I'll say about this is that you see over here, I've got parrot and owl next to each other. Well, that's not a problem at all. Parrot and owl will both go into Ravenclaw. So the fact that these are in this embedded space next to each other means that this is pretty good. What I'm really worried about, actually, is this mess right here. So there's a little bit of a worry of what's going on in this particular portion of the data set. So it looks like we might have to check into this a little bit. So look at the first thing we see here is that someone wrote this as a lion. That's a lion. They just wrote the word lion and then put, I think that's a smiley face. And then, of course, some people say this is a bird. So I think we're starting to see part of the problem here. The data is not exactly clean enough for it to differentiate between these with a level that I like a lot. Now, of course, the sorting hat can be wrong, and that's totally okay. It's still fun and still interesting, and I'm still okay with it. But we need to take a minute here and take a look at what happens when you kind of get data like this. We need to take a look at fixing it. So what are the methods for fixing it? One is manually fixing it, which I found out when the original NIST database was released was a punishment for a single person who had to sit there and go through it, would show entire pages worth of information. I coded the exact same thing where it puts all the information there. And then now I have to pick which one is the outlier or what's the bad information. This was a terrible idea. There's 100,000 images in just these 10 classes. And so I'm wondering, what am I going to do with all this? Do not do manual unless you have something like Mechanical Turk or a large team. But this did not work for me, especially as a weekend warrior project. Another thing I did was I upsized the images to 128 by 128. I took the vectors and upsized them to PNGs at 128 by 128. Maybe there's some details in there that was really important. Nope, that didn't work either. And so I think it's important to say these parts of it. Because a big part, if you come from web, you're going to be like, I'm not used to having two failed efforts before I actually find anything else. If you're coming into this from a data science perspective, then this seems like classical. But one of the things I want people to understand is that we tend to hide a little bit of our mistakes. And I want people who are jumping into this, people who are taking a look at this information for the first time, to feel really comfortable. Everybody you saw talk today failed their way to getting whatever they demoed. I guarantee it. And so the last thing that I did that actually worked is I trained a model to identify terrible data and then help me kind of bring that in as to train the data, to get the data so I could train the other model. So this is like a circular kind of process. Is there text detected? Is it a complete mess? Is it just pure scribbles? So I was able to sort of like semi-train a model to help clean the data set. And I've talked to some other data scientists, and they do the same kind of thing, even using the model itself to help clean a data set, since it's not necessarily a real-world example. And with this, I created, yes, indeed, hello, my Harry Potter nerd friends, the ridiculous data set. That's right. This is available on Kaggle if you want to go ahead and train with it, create a notebook, do some other fun stuff. It was really fun and easy to kind of create this data set. And it ended up with 8,000 to 9,000 images of each class with a really 28 by 28 memory, and it was working great. So this is available now on Kaggle. Please go upvote it, check it out. And I think that's a very entertaining data set. Remember, the goal here is to do something fun for beginners. And so this is available. All this is completely available. So then we have our second portion here, significant data, right? So now we get to move on to what I think is a pretty exciting part of it. But I'm going to review some of the technological things that we heard from earlier today. So that way I'm not just doing a story time. We're going to talk a little bit about code. We're going to talk about a little bit convolutions. We're going to talk about max pooling. So the next step here is let's make a simple TensorFlow.js model and a website so that way we can actually see how this works. So wow, what a great artist you are, Gant. So this is a wonderful picture of a lion. It's a 28 by 28 with a grayscale. That's why it's 1. And that's going into a set of convolutions with 16 filters. If you remember how Lawrence was talking about filters earlier, this is that same filter, max pool, filter, max pool, filter, max pool. And then we connect that to a deeply connected neural network. This is a visual of sort of like giving you what's happening here. And it might seem like, well, Gant, I still don't understand what convolutions are. No problem. Convolutions are these different kinds of filters which help us kind of gather data from a particular image, so that way we could actually get features that the neural network can later on identify. Take a look at this jack-o'-lantern and look at all that noise in the background, all that blurry stuff, all those crazy things with no edges. And then here I'm running it through a Sobel so it can have edge detection on what's going on. And look at that jack-o'-lantern pop out. So now we actually can see the features of the image. We can get those different pieces. We're simplifying and we're getting the information from the data. Convolutions help us do that. Now, after each convolution, we then go ahead into max pooling, where we have this window that goes over and it takes the max affected item from each window unit and then moves it down. And this downsizes the image and then it influences what the features are. Now, when Lawrence talked about it earlier, and when you see this graph, you might think to yourself, okay, so you're taking a little piece of each block of a picture and then making a new picture. Well, that's going to look nothing like the original image at all. And that's how I felt for a long time. But then if you actually see the output, it's amazingly interesting. And I have this video, I have approval from the artist who did this, to show you what I believe is the best visual representation of max pooling I have ever seen in my life. So if you'll indulge me for a moment, I will play this video. Now, if you take a look here, it's been cut into slices, and then he breaks this into 2 different images of a dog. Now, does that look like 2 images of a dog? Yes, it does, but it's already been cut. Now he's cutting it along the axis, just for a moment here. And he's breaking that into 2 different sections. And lo and behold, 4 images of dogs, a quarter of their original size. Would you say that each of those are a dog? Yes, you would. Amazing. So max pooling is effectively doing that. A little crazy, right? Might take a little bit of time to make your peace with it, but we just saw it work, so I think you're going to be okay. So we have the 3 convolution plus pooling layers that do that, take the features out, break them down, make them simpler, and then we flatten that. We stick it inside of a deep layer with 10 final options, and then we compile the model. So what does the code look like for this in JavaScript? This is where if you are new to machine learning, I just want you to sit back and say to yourself, that code is very simple. It's not complex. I might not understand it today, but I know that that's just a few lines of code, and I will understand. If you're used to machine learning, I want you to take a step back and say, that's JavaScript, but I can read that just as easily as I would write it in Python and TF2 with Keras, right? So here we are. We're starting immediately with our 3 convolution and pooling layers. And this is a layers model where we're simply adding a layer with, we'll go ahead and kind of take a look at this. And this is done 3 times. So if I was trying to read this, I'd say, model, I'm adding a layer, and I want those 64 filters. And then I have some parameters here that people who are used to machine learning will easily understand. And if you're not used to it, you can get these 4 lines of code and catch up with the rest of us. And then we have that max pooling portion here where I say add another layer after that with max pooling 2D. And I want it to be 2 by 2, which is like the graph that I showed you earlier, that'll make the image a quarter of its original size. So now there we have it. With these 3 different sections of code, I have my convolution and pooling, and then I simply add the neural network at the end of that. And then within under 50 lines of code, we can run all those thousands of images through this model. And what comes out the other side? Well, that is the draw your own animal and get sorted into the house for TensorFlow.js. So I am going to brave the live demo action here and try my best to actually do this live for us. So let's see what happens. Wish me luck. So here we go. We have Gryffindor, Hufflepuff, Ravenclaw, and Slytherin. And what I'll do here is I'll just draw a little circle. And what's right now is, aha, we can see actually I've set the opacity to each of the 4 houses to whatever's the most believable right now. So it currently thinks that the circle is Slytherin, but I'm going to add a beak. And now, ta-da, I am in Ravenclaw. Look at that. And now I can clear this sketch right now and we'd start all over. Isn't this way more fun than drawing numbers? Let's do that snake though. Let's get the snake going here. There we go. This is snake. Rawr. I never said I was good at this, y'all. There you go. There's a snake for Slytherin. And I will brave. Oh, please trust me. I'm not good at this. Let's see if we can do a Gryffindor lion here. This. As we know, a circle kind of looks. Oh, that's scary already. And then there's a mane, right? There's a mane around a lion. Give it a little tail. Oh, we're getting a little here. And yes! I have done it! So there you go. Now we are sorted into Gryffindor for this setup here. Lots and lots of fun. You can go check this out right now at aisortinghat.com, which is a fun little domain that Infinite Red picked up so that we could have this out there for everybody to experiment with. So there we go. Don't forget to check out aisortinghat.com. Goodbye, magic. Hello, science. We were able to figure this out. Got 8,000 graphics. We generated from those 80,000 plus graphics a 400 kilobyte model, a little model that sits there and immediately checks what that canvas drawing is doing, and then immediately tells us what particular house that we're getting sorted into. So there we go. We have a simple TensorFlow.js model and website. Well, as you know, I told you earlier, I don't think that it's good enough to just stop there. I think that the most important thing that we can do next is that we can do that +1. And that +1 helps us say, all right, now I'm going to do this. So one of the cool things you've heard about or seen quite a few times today is transfer learning. And transfer learning is a very simple, well, we've got another wonderful Gantt graphic here, so my apologies. But we've trained all those filters, just like Lawrence was talking about from earlier on, but they're connected in to identify what house someone belongs into when they finally comes out of those features that it's identified in an image. Well, we can easily stop that. And then what we can do here is take that convolutional system that we've trained and move it on over to a brand new neural network that we are going to train. It's just going to be the tail end of this. So we have all those amazing photos from Google's Quick Draw, but we don't have a lot of really cool drawings of the amazing people at Starfleet, right? So we have Starfleet, Klingon Empire, and Ferengi Alliance. I'm sorry, I am nerding out really hard on y'all. And to be honest, I have really been watching Star Trek Next Generation a lot lately. So this is sort of like what I'm thinking about. But the problem is I don't have a hand-drawn data set for these particular icons. Well, do I have to worry about that? No, I have an existing model that looks at drawings, and I have the potential to do transfer learning. So we're going to boldly nerd where no nerd has gone before. And I simply drew the worst um, 50 images of each class. That's 50 images of the Starfleet badge and logo. So that's set there. I did the same thing for Klingon. I did the same thing for the Ferengi. So now I have this small 150 training image data set, way smaller than our original 100,000 images, correct? But can I get that sort of benefit here? Yes, I can load the original model and then shave off that neural network that previously existed. And so you see that here inside this code where we're shaving off, we're saying go to the last pooling layer and stop there. And so we have this new layer that doesn't have the neural network attached. And so now we can take a look at those and we can add our own new network on the end of that, which is going to train specifically on the new 150 images. So you say, Gant, can we see this? Is this a real thing? Did it work? Well, good enough for you. It's still here. So let's go ahead and take a look at this right now. So I'm going to go ahead and take the AI sorting hat that we saw a moment ago. And then down here at the bottom, we see learn how this was made. And I have a boldly go here. So as we click on boldly go here, we're going to get this cool new interface that's taken the trained model. And here's something great about TensorFlow.js. I am going to be training this right now with you watching in the browser. So I'm going to load those 150 training images. So I click that. Then I'm going to create the model, which has no data run through it. Click that. And now I'm going to create the transfer model between those two and then get that set up. And then lastly, I'm going to click this button and my 150 images are going to be used to train this new network. As I click there, and it is training on my machine. Apologies if anything happens here. And look, there we go. So now we need to see, are we in Starfleet? Oh, that one's pretty easy. I don't even have to finish the image. Okay. Klingon. By the way, I am not an artist or a scientist. I don't know what I'm going to do here. But let's see if I can do this. Please don't be terrible at this game. Oh, I didn't even finish it. Klingon. Nice, done. Oh, went back to Starfleet for a second. But yeah, there you go. So there's Klingon. And then last but not least, can I draw this crazy Ferengi symbol? I don't know. I really don't know. Okay. Then we've got the same thing, like mirrored. Please. Hey! I didn't even have to finish drawing it. I'm not that good. So there it is. The Chicago Bears are part of the Ferengi Alliance, is what we see here, is that logo right now. So fun enough. We're able to go ahead and check that out. So yes, you can go to aisortinghat.com/transfer, and then on your machine, whatever speed you have, click those buttons, and it will create right then and there your own transfer learn from only 150 images. All of this, of course, is open source, and it's a lot of fun. So success. We've gone from the magic of Harry Potter to the science of Star Trek. It's been an exciting adventure for that. Now, one of the things I'll say that the training's faster, the data is smaller, and we're capable of creating brand new things by using this. Now, as Lawrence referenced earlier, be careful whenever you're doing transfer learning, because even if your data does not have any kind of inherent bias, whatever you might be training off of, that model, if it's kind of biased, that'll come through directly into your training, because what happens here is we weren't re-editing or re-modifying those convolutional layers. They were effectively locked. We can unlock them, and then we can train to do some fine tuning. For this example, maybe that's a little bit beyond, but it's a lot of fun. Okay. So we've been able to expand and escalate our idea, which I think is a lot of fun. So let's review what wild adventure we just had We started off with TensorFlow.js, which I am extremely excited about. And it's one of the greatest things that we're able to move to these edge devices. We could play. We can get these instantaneous examples where I say, go try it right now. And guess what? If all of you download it right now, you're not hurting my server. It's running on your machine. So, server costs. Good luck for you. I created the ridiculous data set, which is available on Kaggle. Please go upvote it if you can. I would love to get like a bronze medal for that data set or whatever kind of cool things happen. I'm all about my titles, y'all. I need those titles. And then we created the sorting hat, which is aisortinghat.com. And then we took that model, which has seen thousands and thousands of examples, and we created Transfer Trek, where we just made something with only 150 images. And that's really cool. So if you really enjoyed this, if you enjoy the way I kind of like instruct or explain things, plenty more of me to go around. I have a course completely on TensorFlow.js, academy.infinite.red. It is a fantastic course. DM me if you need a discount code. I will totally hook you up. As a matter of fact, I'll go ahead and send one out after this. And we'll get you a discount code if you want to take that course. It's a really fun 3-week course to take you from a web developer perspective into the world of machine learning, and you start building some cool and interesting things. And then, of course, as several people have lovingly said, and I really appreciate it, I finished writing an O'Reilly book, which is a lifelong dream for me. I've always wanted to write an O'Reilly book, and it basically sat down and wrote itself. So inside the O'Reilly book, we do cover how exactly all this works in chapter 11. Lots of fun. Some really cool stuff in chapter 12. But that is available for pre-sale, I think, as of today or so. And there's the link that's there for that. So please, please, please check that out. And follow me on Twitter. I promise you, I will do all kinds of crazy, fun experiments. I have some really fun things coming up soon. And I love showing these to people. And I love, love, love going on Jason's Made with TF.js show and tell. So please follow Jason, Jason Mays, and watch the hashtag Made with TF.js. If you do, you'll see all his stuff. You'll see all my stuff. You'll see all kinds of really cool things where you can see what I've got in the pipeline for you next. And with that, thank you everybody who paid attention, has questions, and helped me go ahead and speak here. All the previous speakers for being so inspirational and so welcoming. Thank you.
Awesome. Great presentation and very fun demos there, Gant. A lot of great stuff. It was so much fun. Like the comments were abuzz with all the different data sets and stuff. Like our previous speaker, Lee, she LOL'd at the ridiculous data set.
I found my home. I found my fellow nerds. That's what's important.
Yes. And then like Carly, who's backstage, she became the best aunt ever when she was sharing your links out. Everybody was having fun nerding out with your content. If you do have questions, we do have more opportunities for questions for Gant here. There were a lot of comments about questions for the project, such as like for the AI sorting hat. How about what you were doing was all based on drawing and stuff like that. So Carrie asked, like, what about using voice? So voice.
Yeah, I love this idea. And then I kind of what's great about this is it's a great way to get involved without being wrong, right? If you go draw a lion and it's the most beautiful lion ever and it gets sorted into the wrong house, okay, but I think like that's a great idea. And I think the same 4-piece formula that we used here is that we are starting to see it's very important to choose relatable and interesting things. So doing it with voice, doing it with that, using these particular icons. The web world has always been really good at this, right? It doesn't take long for them to create some funny or silly or cool website on these things. And now seeing that merge with this revolution of AI, we're going to see some really cool stuff in the next 5 years.
I'm looking forward to it. That's pretty exciting. Yes. On the sorting hat and kind of what you were talking about a little bit, Raj asks, how about users validating like if they actually drew a lion and it detected it incorrectly, for example?
I love this idea, and let me just say, it kind of comes into the world of TensorFlow.js a little bit more. For instance, Lawrence has this data set of paper, rock, scissors, right? And he, to do his paper, rock, scissors data set, he did 3D hands of all kinds of different levels of masculinity, different skin tones, awesome, cool stuff like that. And he's this 3D models. But what I would love is a world that's just like what Raj is talking about. What about a place where I can choose to give you, whether or not, some extra training data that kind of comes in, gets brought in there, and then the improved data set, and maybe you get your name inside of like, a leaderboard. I've donated 1,000 images that have been approved, and this and that. I think that this is the future where you wouldn't have, the incentive for a server-based or sort of like a financial-based system. You wouldn't want to have that stuff out there. But with TensorFlow.js and fun ideas like this, yeah, I love that idea. And I think that we need to see somebody kind of build that project and demo it next TensorFlow everywhere.
We did have a fun suggestion here from the audience. Alex was asking did O'Reilly let you draw the animal for your book cover? There were some other fun comments about how great of an artist you were. So you were doing a great job for using your mouse, being live on camera.
I appreciate that. But they get no better non-live and with a pen. They're just the same quality. Anyway.
Same quality.
And O'Reilly, didn't let me choose. One thing I did say, I said, like, hey, can it be a reptile? Because two of the best TensorFlow books that I really like are already reptiles on the cover. And so I said, I just want a reptile. So it will be a turtle. Now, I'm from New Orleans, so it should have been an alligator, but a turtle will do.
Turtle will do. Awesome. I did want to reflect back on something you mentioned earlier, and this was something that Lee brought up in her presentation as well, about failure and how everybody with all of their experiments, there is some variance of failure. And like, Lee acknowledged it, like as she was building out her project, and you were alluding to that as well. Do you want to dive in a little bit more about failure?
Yeah, absolutely. It's different from what you're used to. The whole concept of probabilistic outcomes and training and graphs, you can spend entire weeks doing just to find out that it did nothing. And it's a little bit alarming at first. And for instance, at this talk in 2018, I agreed to the talk and I started training the machine for it. And I watched the accuracy go down and the loss go up. It just stayed like terrible the entire time. And then I came back to it after I was like, this thing's not getting better. This isn't going to work. What am I doing? And kind of stayed on top of it, read up a little bit more, learned, researched, and then I had this amazing feeling, this amazing moment where I come back and it's in the cloud and I look at the stats and there it is. Just the accuracy is fantastic. The loss is crushing down into it. And it's like, that's right. That's what the graph's supposed to do. It's going to work. And then I pulled the model down immediately, tested it out, and it immediately worked. I was so happy because then I could actually do my talk. It was going to become a talk about how AI can fail, I guess. I don't know what it would have been if I didn't do it. But it was so interesting. And the trick is it's easy to hide that part. So easy to hide that part. You just see the successful model that was iteration 3, 4, 5. We see this a lot in web, but I think it gets exacerbated a little bit in machine learning. So I just want people to say, hey, if you're not failing, you're not growing. It's totally okay.
For sure. Great point there. Yeah, if you're not failing, you're not growing. I wasn't able to find the question for for Lee, so I went ahead and quickly made it. Do you think it'd be a good fit for me?
Yeah.
And so we do have people in the comments, in chat and stuff like that, asking about the GDE program.
Yes.
Acknowledging like how many amazing GDEs we've had on yesterday and today.
Yeah.
What any insights or thoughts you'd like to share about being a GDE?
What a well-run program to be a part of. You're immediately connected to a lot of great information. You have these well-scheduled meetups where you get to interact, your voice is heard. Even I remember one of the GD meetups, one person was saying, I think we can be better about this. And I was like, this isn't just fanfare. This isn't just anything. These are real discussions with intelligent people who are having a great time. And I'm dying to go to a summit. I've been waiting to go to a summit. I had my daughter get born, and then the pandemic happened. So I'm still like waiting to finally go to a summit. But I've talked to so many GDEs, and they have a person who says, like, if you meet 5 people who are successful and you hang out with them, you're going to be the 6th successful person. Being a Google developer expert is a perfect plan for setting yourself up for success.
Awesome. Great to hear. And yes, I agree. I can't wait for our in-person summits again to bring everybody back together. It is very fun. We do, I mean, beyond the networking, there's a lot of great knowledge share, like all of these amazing experts in one room. It's very fun to be around. So.
Yes, indeed.
But
soon.
Yeah, soon. Hopefully, fingers crossed. So again, thank you so much, Gant, for joining us. And hopefully you can stick around a little bit longer in the chat, answer some questions. There were some more feedback, and then this way you could also review the reactions to your demos. There was a lot of great ones in there. So thank you again for joining us, Gant.
Absolutely. Have a good one.
Cheers. Awesome. Don't forget to leave your feedback for Gant and all of our other speakers here. Remember, there's the 2 at the end, TF Everywhere survey. And up next, we have a great Google developer machine learning expert, Pooja, who is currently a machine learning engineer with Stripe. And she'll be talking about how to become a machine learning engineer. So please help me welcome Pooja.
Can you hear me and see me okay? Okay, I've gotten a yes from the chat. Great. I'm super excited to be here. Thank you for having me. I'm Pooja Rajan. I'm a machine learning engineer at Stripe, a fintech company. And outside of work, I'm a Google machine learning developer expert and a Google Women Tech Maker. Both are really great programs, and I encourage you to check them out. Today, I'm going to talk to you about how to become a machine learning engineer. I had a lot of help finding my way, so I just wanted to give back by sharing my experience. This is a lightning talk, so I'll be speaking at a high level for about 15 minutes, and we'll have time for about 5 minutes of questions and answers at the end. Since I won't be able to go to too much detail, I'll share a few links where I write about this topic in more detail at the end, and stick around to answer any questions in the chat afterwards. Before I tell you how to become one, I want to make sure you know why you should become one. I'm hoping this section helps motivate you through the process of becoming one. I tried a variety of things before finding my dream job as a machine learning engineer. As a child, I had no idea what I wanted to be when I grew up, and I changed my major 7 times in college. I worked as a data scientist, a quantitative analyst, and a data engineer and software engineer before becoming a machine learning engineer. So it was a journey. But let me tell you why I love waking up and going to work every day now. First, there's a lot of open questions in machine learning. The answers to many questions can be found on Google, but in machine learning, there are a multitude of unsolved problems. If you solve the problem, you might be the first one to do so, which is really exciting. There are a lot of applications to many different industries, including finance, tech, healthcare, and even more. So if you have a passion, then you can specialize in that domain. And if you don't quite have one yet, then you can explore and move between industries, like how I did. I worked in finance previously and then ended up moving into the tech industry. As a machine learning engineer, you can also use a variety of skill sets. So there's coding, system design, communication, math, statistics. It's never boring. You're always trying to grow and develop in a multi-dimensional way. You can feel like an academic without the perils of the ivory tower. The path to becoming a PhD student or professor is sometimes full of poverty and politics. And as a machine learning engineer in industry, I get paid to learn and build solutions, which I love. Oops. Here's a preview for the next slide. So the next thing is impact. You have the opportunity to make and or save companies significant amounts of money as an individual, which is compounded by a team. The community in AI is also still pretty small and close-knit. We like talking and learning from each other, both in person and online like this. So if you like hanging out with other machine learning engineers, you'll enjoy working with them too. Machine learning practitioners gather at meetups, hackathons, conferences, which gives us an excuse to travel to in non-COVID times. So I hope to see you at some of them in the future. Last but not least, career options. AI is a growing field and your career options will grow with it. Imagine 10 to 20 years from now, you'll be one of the most experienced engineers in this field. After a few promotions, you'll have the option to move laterally as, you could become a data scientist, a data engineer, or an ML-specific product manager. And after a few promotions, you'll even have the option to become, a tech lead, an engineering manager. You have the option to be fully remote. You can work from home or travel or be a freelancer. There's honestly nothing stopping you from becoming an executive or even a founder and an entrepreneur one day either. So lots of options and lots of good things. Remember, it's a marathon, not a sprint. Like I mentioned before, I started as a software engineer. Even after graduating from college, I started as a software engineer, then completed a boot camp and worked as a deep learning engineer at a tiny 20% startup before I landed my current role as a machine learning engineer at Stripe. It took me 3 years, 300 plus job applications and 100 plus job interviews and like 10 graduate school rejections even, and many, many more job rejections. So keep going. So the first part of this talk, I'm going to focus on how you can become a machine learning engineer if you're still a student. And then if you're not a student, don't worry, the next slide is for you. I'll talk about switching from being a software engineer in industry to becoming a machine learning engineer. But if you are a student and are still in school, lucky you, because the machine learning field is still really academically oriented. You're in a really good place to learn a lot. I'll break down the preparation into the academic portion and then the industry portion. Firstly, I just want to mention that you only go to college once. So you want to do the things that you can do in college and take advantage of those things that are easy to do while you're in college and harder to do once you graduate. This means like taking classes, doing research, participating in extracurriculars, considering applying to grad school even. All of these things are harder once you're working, so make the most of your time in college. I'll start with coursework. So machine learning requires a foundation in a variety of subjects. So computer science, mathematics, and statistics are like the basics. And you want to start with the introductory courses. And since most ML engineers do have a master's or PhD degree, which again, I don't, so don't worry if you don't, do try to level up and take a few graduate level courses in your schedule if you can as well. ML is a multidisciplinary field. I recommend specializing in a subject that you're really passionate about as well. So you can use this to satisfy your non-major requirements. So for example, in college, I actually took sociology classes and did sociology research in a subspecialty called quantitative or computational sociology. And it was really interesting. Biology, neuroscience, and finance are also a couple other non-engineering fields that I can think of that have quantitative specializations and ML applications as well. My one tip for you to walk away with for coursework is to enroll in the classes about data structures and algorithms and machine learning fairly early because they help with the interview prep and they'll also help with your research. Which leads me to the next section, research. Take advantage of the opportunity to do research when you're in college because it's really not accessible after you graduate. And it's never too early or too late to start in your academic career. The research experience will teach you to answer open questions and read papers, which are really applicable skill sets for a machine learning role as well. You can do research, during the school year or over the summer too. The end goal you should kind of think about is try to have some sort of output that you can show off to your future employers. I personally had a honors thesis, and I'm still really proud of it. And I really like having something to show after, the extra hours I put in after class on my research. If you don't have the option to do a thesis, it could be, something as simple as contributing to a GitHub, a blog post, or, if you can, even a published research paper. My tip about research is also to attend academic conferences. It's much easier to get in as a student than after you graduate, and you'll have the opportunity to meet a lot more people and learn from those people as well. So the next thing is extracurriculars. So if a club or project team related to machine learning exists, join it. If not, start one. I was a member of the data science project team at Cornell when I was there. And after graduating, I founded the US chapter of Women in AI. And I wish I started something like that earlier, something similar in college. And this will give you the opportunity to meet others with your passion. It's not only more fun to learn together, but it's also a useful network for the future. The last thing under academic was grad school. And this is a really personal decision. It's a whole nother can of worms. So I won't go into too much detail, but talk to your academic advisor or research advisor for personalized advice. I also encourage you to talk to current graduate students at your school about their experiences as well. Industry experience is also really important, even when you're still a student. So get off campus to get a taste of the real world. Get an internship, attend and organize hackathons, conferences, meetups, and other events. I know this is a lot easier in non-COVID times, but you can get off campus virtually these days. So try to be involved like you are today and explore the internet and find your niche. And apply for an internship at a tech company. I admit getting one is easier said than done, but my advice to you is to cast a wide net with companies and roles. Your career is a marathon and not a sprint. That's a theme that I've been, repeating over and over today, but I interned as a data scientist and a quantitative analyst, and then somehow got a job as a software engineer before becoming a machine learning engineer. All of these roles were a little similar, and they can still lead to the machine learning engineer role. I feel like every internship I had, even though it wasn't the title that I was aiming for, it still prepared me for the role. And that's really helpful. The more times you apply and the more times you interview, the more likely you'll just get an internship. So just apply anywhere and everywhere. Every rejection is a step closer to an acceptance one day. So try to reframe your mindset like that. Interview prep is really important. One of the sad things is that not everything that you learn at school or on the job is going to prepare you for your interview. You're going to have to set aside time and prepare for your interview specifically. And if you start preparing after you get an interview, you're a little late to the party. So start preparing before you even start applying. Software engineering interviewers primarily ask data structures and algorithms questions. Machine learning engineer interviews consider statistics and ML questions fair game on top of those data structures and algorithms questions as well. Let's say you've already graduated and you're still stuck. That happened to me, so it happens. Don't worry about it. If that's you, then consider a boot camp before applying to grad school, which is much more expensive. I personally did the Insight Data Science AI Fellowship after graduating. Unfortunately, they're not running anymore because of COVID, but there's other ones out there. After the boot camp, I got a deep learning engineer job at Node, which is a small AI platform company, and it ended up being acquired within my first year there by Sugar CRM. And I stayed to help with the transition for a little bit before leaving and joining Stripe as a machine learning engineer. So that was my journey. So if you've already graduated, not to fear. I technically switched, to being a machine learning engineer after graduating as well. So it's definitely doable. In this particular part, one thing that's really nice is all of these options that I'm going to talk about can be explored in parallel. So, whichever one works out for you first, you can, go with that one. The first option is to work on a machine learning project as a software engineer. The number one thing that software engineers lack when it comes to applying to machine learning engineer roles is real world work experience. I see way too many engineers making the mistake of listing multiple online courses on their resume when recruiters are simply looking for past projects. Save your time and money and get staffed on a machine learning related project as a software engineer. All you're probably missing is a few ML related lines on your resume and projects that you can talk about in your interviews. Machine learning engineers often collaborate with software engineers anyways to build an end-to-end system. So if you're a back-end engineer, front-end engineer, full-stack engineer, then you can get machine learning exposure from being staffed on one of these end-to-end machine learning projects while still staying at your day job. Real-world work experience is significantly more impactful than taking an online course when you write about it, because you'll be able to talk about it in your job interviews in more detail. You can also try to transition internally at your current company. This is a really good option to consider because you have the advantage of knowing your company's internal tools and technologies better than external candidates. Think of it as having like a leg up. Another option is to apply for jobs like software engineer, machine learning at big companies. There's these category of machine learning and software engineering jobs that require both skills. They usually have the job title of software engineer and machine learning in the job title. The roles with software engineer in the title will weigh your past experience as a software engineer much more positively than like traditional machine learning roles or even research engineer type roles. And my last tip is to apply to startups where software engineering and machine learning skills are needed. That's what I did, actually. So I think people too often underestimate the experience of working at a startup. I think it's one of the best environments to transition to a new role. I personally, how I did it was I went to Crunchbase and searched for all the AI startups in the Bay Area and ended up cold emailing all the founders, which led me to my first ML specific job at a tiny startup. And I wouldn't be where I am today without my experience there. Last but not least, it's not listed on the slide, but there's also always the option of applying to grad school or boot camp, but I'll skip that here because I talked about it a little bit in the previous part. And again, that one is a really personal decision. Next, I'll talk about the technologies that I use as a machine learning engineer on a daily basis. As you can see, machine learning engineers use a variety of technologies. Each one is unique and each role is different. I personally code regularly in 3 languages, Scala, Ruby, and Python, and I also work with open source technologies in addition to company-specific libraries on a daily basis. So being a machine learning engineer means a lot more than just modeling using TensorFlow, which is also really important, but it's a big world. I also use Spark, Kafka, and Flink for processing data in batches and streams. So this is where my past experience as a data engineer actually came in handy. And I also use Pandas, scikit-learn, matplotlib. It's kind of the standard Python machine learning stack regularly. And that's where my past experience as a data scientist actually came in handy. There's also application-specific libraries. I previously specialized in natural language processing, and as a result, I became really familiar with NLTK and GenSim. So those two are natural language processing libraries, and there's actually roles out there that you can look for that are specific to NLPs, and it's called like natural language processing engineer. So in that case, you might want to take a look at those. And computer vision has their own stack, reinforcement learning has their own stack. I'm not as familiar with those, but I encourage you to kind of take a look and become familiar with some of these technologies because they'll be helpful in kind of building real world applications. This is the end. Thanks for listening, everyone.
Awesome. Thanks so much, Pooja. Great presentation. I learned some interesting things. So did you begin your, you talked about starting from undergrad, going to graduate school, that kind of stuff. So were you set, immediately once you were in undergrad, like I want to be a machine learning engineer? Because I know you said you jumped around with careers and stuff like that. So what inspired you to become, machine learning?
Yeah, that's a really good question. So I knew I wanted to do something that was really quantitative and as an engineer, but I didn't quite understand the difference at that point. I mean, this was also it was a while ago, right? Like there wasn't a clear distinction between data scientist and machine learning engineer at the time. Like it was a bit of a mix, and data engineer and all those roles. And so I didn't quite know, but I figured it out by trying all of those things. Like I didn't think like, oh, I just want the machine learning engineer job. I actually was like, oh, data science, like I know it's similar, let me give it a go. Like quantitative analyst, yeah, it sounds similar, let me give it a go. Software engineer, it's related. Data engineer, it's related. And eventually each step of the way, I like picked up the pieces that I liked and it just like converged at machine learning engineer.
Awesome. I was also playing a little bit off of your bio there where you talked about playing chess and then saw how the artificial intelligence beat the grandmaster in chess.
Yeah.
And that's kind of what also inspired you to get into machine learning, just to see how it was done. And
yeah, I remember being completely floored back then. I remember, training when I was playing chess competitively and playing on the computer and being like, how does it beat me every single time? And just being, confused just by the computer itself. And then seeing that it beat like the best human ever, I was in awe. And that kind of is what set me off on this path. And it actually led me to start thinking about algorithmic trading, which, in the end actually wasn't for me. I ended up transitioning into the tech industry, but it was these building blocks. And that's what I kept saying kind of in my talk, that it's a marathon, not a sprint, to kind of find your dream job. And I'm hoping that, that resonates with some people. And I hope everyone can find their way at some point.
Definitely. And I plus one that, because it's, everybody has, some form of that story, and, as they progressed into figuring out what it is that they want to do when they grow up, kind of thing. Like, I know we're all still figuring that out.
Yeah.
So, very cool. We did have some other fun questions from the registration I'd like to drop in for you here. So what is the most exciting niche in the deep learning space, according to you?
This is a really hard question. I feel like I touched upon this in the presentation. There's so many exciting niches that I feel like whichever one's most exciting to you depends on what's your passion and like what you're really interested in. For me, I really love natural language processing and looking at, applications of reinforcement learning and NLP and things like that. But that's because I really love reading, and that the RL part comes in from, playing chess and there's this exploitation paradigm. But I also really like NLP because I really love reading, and I want to pass that on to computers and help them, understand text better. But just to mention something that's really crazy and out there, I think applications of AI in art and music are particularly interesting, and kind of it's really cool to see the intersection of two industries that are traditionally pretty far apart, something that's more creative and something that's more scientific. And I think that would be a really good time to mention the thing that got me into it was there's a TensorFlow Magenta package. So if anyone hasn't played with that, I think it's the coolest thing ever, and you should go check it out.
Definitely. And since you as you mentioned, back to art and music and stuff like that, we had Vikram earlier this morning who was talking about how to do pretend to be a composer like Bach using machine learning. And then yesterday we had Tan Mei who used machine learning to generate a song, and then actually had a different music artist perform the song that was generated by his AI, the machine learning AI. So it's some very cool stuff there.
Yeah,
some projects
for sure.
like you're talking about. Another question here. How did you overcome your most challenging project, whether it was school or work? What are some tips or?
Sometimes it depends on the project, but I think the best advice that I've received that I try to put into practice every single time is breaking down a problem into smaller problems. I think this is frustrating advice because you often get it when you're doing coding interviews or something like that. They'll be like, here's a really hard question, just break it down into smaller problems. And you're like, how do I even do that? But sometimes you just have to take a step back. And once you do that, it really does get easier. I also think it helps to talk to people when you're challenged. If you're particularly challenged and you're stuck, don't be stuck by yourself. Try to get some help, talk through it with someone, even if they don't know the answer. I think that action of talking to someone, rubber duck, having a rubber duck helps a lot. So those are my little tidbits.
I like that term. I've not heard that term before, the rubber duck.
Really?
Yeah. I mean, I've used that in the past before, where try to just. What's worked for me is I'll distract myself from the issue that I'm stuck on, but then it just makes so much sense, the rubber duck idea, or I'm talking to somebody else. It might not even be about what the issue I'm stuck on, and then all of a sudden that clarity moment hits, and sorry, I'll be right back.
Yeah.
So very cool. I'm gonna to borrow that one, rubber duck. I like that one a lot. And then we had many comments like this about marathon sprint advice. There's a lot of different things that a lot of our viewers are working on. Many of them today were intro to ML, and so they definitely, leading up to this, having your talk about how to become this machine learning engineer. So we had a lot of great topics about where to get started in machine learning and all this, but really wrapping it up solidly with how to become this machine learning engineer. So I would, everybody is very appreciative of all the amazing tips that you gave, and from your experience, as well as what you've seen in the hiring process. So there's a lot of amazing stuff. There's so many fun, positive comments here. Having trouble trying to find any questions.
Well, I'm really happy to hear that. I think just like something to add there, I felt like I had a lot of imposter syndrome when I was going through the process myself. I felt like I wasn't necessarily cut out for it for one reason or another. And so I just want to encourage everyone to, if you feel that way, just keep at it. That it's like everyone feels that way at some point, but you kind of just have to keep going, because I guess there's that saying, right? Like anything in life that's worth having, like it's hard. Like it's going to be a tough process.
For sure. One other question here. So what sparked you to become a GDE?
So I actually was inspired to be a GDE by other GDEs. So I met Vikram. I forgot how. I think at a GDE event, and I also met Lei. So who was it? Gant that spoke right before me. Gant.
Yes.
I think I remember like hopping on when he was talking about, or maybe it was you, like who you surround yourself by really matters, because they inspire you to, keep working on something, or just like give you ideas on what to do in life, or just, keep growing as a person. And I felt like that's what really stood out to me about the community when I like met people at events and they told me that they were GDEs, and I was just like, wow, I really want to get to know them. I'd like to, hang out with them and talk to them, and that's what sparked me to become one.
Awesome. That's great to hear that the community had that effect on you, just surrounding yourself with these other awesome experts. And very cool. And obviously you were qualified as an expert. With another question here. Yes, here we go. A word of advice or wisdom that you would like to share with the audience about TensorFlow or machine learning. I know you had some great ones in your talk, but anything that wasn't in your talk that you'd love to share?
Yeah. So many things are actually coming to mind, and I'm like trying to pick which one to share. The one thing that, like, I mentioned that there were a lot of tools and technologies on one of my slides, and I just want to mention, like, this is also TensorFlow specific. The machine learning field is constantly changing. Like TensorFlow, even as a library, I see like it gets updated like every day, every week. There's like some big news, but there's like small updates like just so often, and it's hard, but it's part of the like job to kind of keep up with new things in AI. So I really encourage people to, have a growth mindset and not feel like learning is a hassle, but be really excited to see what new things are coming out, and like try to stay up to date.
Awesome. And let's see, there's just a lot of positivity through here. Yeah, like, thank you so much for sharing. Thank you, Pooja. Just highlighted, there's so much positivity in here. So there's a lot of great stuff that you shared. And so thank you so much. I'm trying to see if we have another question in here. Let's see.
I was really debating whether to talk about a technical topic today or do something that was more like career oriented. So I'm really happy to hear like the positive news. I just wanted to share what I thought would be the most useful during this time. And I know, COVID has really impacted a lot of people's careers, and I thought this might be more impactful than a random technical topic.
Definitely, yeah, and it was a nice way to wrap up with all the content that we had, where it was like, here's how to get into ML. Like yesterday, we had a lot of different examples and some fun, I would say closer to 201 kind of level on some of the talks. But then, today there was a lot of getting started with TensorFlow.js and a lot more new different things that you can do with TensorFlow. And so it was great to wrap up with how to become a machine learning engineer, just kind of like, put the capstone on everything here. So thank you so much for submitting that too. It was great to have that as something we can do in here.
Yes, thank you for having me. And thank you everyone else that's listening for listening.
Definitely. Thank you so much. And do you have time for one more question? Or
Sure, yeah.
Awesome. Okay, so there's this one here. What would you say is the most strange place, a project that you've seen for a TensorFlow model that's been deployed?
There's kind of this, I don't know if Lawrence already gave this talk a few days ago, but one of the coolest stories that I heard was the application of using TensorFlow on, was it cucumbers in Japan or something like that? Being used in agriculture in general, I think is really cool and like kind of forgotten about because agriculture is traditionally a very like manual kind of job, right? And so there was this project that I heard about where they were able to separate some vegetable automatically using computer vision by seeing, like, looking at the shape of the vegetables. And like the family that did this, like they hooked it up. They just used TensorFlow. They weren't like a tech company or anything like that. This was just like a standalone family. And they connected the software to their hardware like machine and they figured it out. And I just thought that was really cool. Just shows like how accessible machine learning is becoming. And there's so many applications that we haven't even thought of.
Definitely. Awesome. Yeah, I'll have to look into that project. I must have missed that one. But thank you so much again for sharing. It was a pleasure having you, and having you help wrap up our event. It was great to hear your insights on how to become a machine learning engineer. And I know the audience was super positive about it. If you could stick around in the chat, maybe answer some questions, receive the feedback, that kind of stuff like that. It'd be great. But again,
I'd be
thank
happy
you so
to.
much for joining us.
Yes, thank you again for having me, and thank you again for listening.
Awesome. Cheers.
All right, have a good day.
You too. Awesome. Thank you again so much, Pooja. It was great to learn about all this stuff. Again, please leave some feedback for Pooja and all of our other speakers. TF Everywhere survey 2. Remember the 2 at the end. Yesterday, it was the same link, only without the 2. So please leave the feedback. It helps us curate and build more events like this one that you watched today and yesterday, as well as this feedback does get back to our speakers on how they can improve their talks or any kind of feedback around that at all. And with that, let me get my slides back up here. So I think let me buzz through really quick. I'm at the wrong spot. My slides didn't advance. All right, let's try this again. Perfect. All right, don't forget, there are TensorFlow user groups that are available to join. If you don't have one near you, we are more than happy to have you start one near you. You can learn more about them at tensorflow.org/community/groups. We do have the free hands-on workshop learning, Tori, if you are interested to learn more about TensorFlow and TensorFlow on Google Cloud, as well as other machine learning tools that are available with the Google Cloud suite of products on the platform. You can go to the link here, google.gle/tfeverywhere-quicklabs, where you can redeem free access to hands-on learning on QuickLabs. Keep in mind that the link does expire March 6th. So all you have to do is redeem it and start to take the first lab. Once you've completed the first lab, it'll give you access for the next 30 days. If you do happen to have any issues whatsoever in trying to redeem this, reach out to support@quicklab.com. And as well as if you happen to have any issues at all while you're taking the labs and completing quests, you can always reach out to support, and they're more than happy to help. I know we had some comments earlier about any interaction that they've had with the support team with QuickLabs. It's been great. So that's great to hear as well. And we're more than happy to bring this free learning to you. Again, submit your feedback for yesterday as well as for today. We'd love to have your feedback so that way we can help curate better events, more events, as well as provide this back to our speakers as well. And with that, thank you all so much for joining us for the past 2 days. It's been great, learning from all of our different speakers, helping all of you network together, and all the fun conversations that have been had in the chat. Keep it up. We're happy to have you here. And thanks again. And we'll catch you next time. Cheers.